Hey, hey, ja, ja. Hey, hey. Ja, ja. Hey, hey, ja, ja. Hey, hey, ja, ja. Perfect. Eigenlijk die tweede insertie, toch? nummer 3. Ik hoor mijn eigen niet. Ja hoor, want namelijk onze videovrienden wilden ook even nog een laatste audiotest doen. Dus vandaar dat dat we ook even gewoon opengeschoven moeten worden. Dit is 3. Zodra deze prima is voor jou, zet hem lekker uit. Want dan heb ik alvast 4 in mijn... Nummer 4, nummer 4, nummer 4, nummer 4. 1, 2, 3, 4, hoedje van. 1, 2, 3, 4, hoedje van papier.
We still have a few empty seats in the front. Please don't be shy, come forward, fill the seats. We have a full room and we have lots of exciting news for you today. So, my name is Angelique van Ombergen. I'm a scientist here at ESA ESTEC, but I'm here today in another capacity. I will be your moderator throughout the day and also in particular for the first panel. So I'm out of my comfort zone, but I think that's what space is about, going out of your comfort zone. And we have a lot of very nice and very important people also to talk a little bit more about that. I would like to give a very special welcome to Josef Aschbacher, the Director General of ESA, Dietmar Pilz, Head of ESA ESTEC and Director of Tech, Wendy Verkleij-Eimers, the Mayor of Noordwijk, Pedro Duc, a former ESA astronaut and Minister of Science in Spain and ex-com chairman of the European chapter of the ESA, which we're going to hear more about today. Harm van de Wetering, Director of the Netherlands Space Office, and Kim Regenery of the Space Generation Advisory Council in the TU Delft. There's also Meindert Stolk, the Deputy of the Provincial Executive of the Province of Zuid-Holland, Renate Beausoleil, Senior Policy Officer of Zuid-Holland, and Roberto ter Hark, Space Alderman of Noordwijk, and we have Dennis Speet and Solange Kleutjens from the Amsterdam and Partners. A very special visit will come to the Netherlands next year, and it will mark a very special year in Dutch space history. We have a very special guest to talk to you more about that today. Please give a very warm welcome for André Kuipers.
Thank you very much. A real pleasure to be here in the Netherlands. This picture I took on my second flight, and it's always nice. If you come from a small country, always good to see your country you can see it in one view. I start now in English. I will switch to Dutch. My presentation will be for the British media or whoever will not understand the Dutch. It will be there available for everybody. Ik ben hier om iets bijzonders aan te kondigen. We hoorden het net al. Volgend jaar hebben we het 35e congres, het Planetary Congress van de Association of Space Explorers. The Association of Space Explorers, I will talk more about that. Het blijft switchen natuurlijk, hè? Het is ESA. De Vereniging van Ruimtevaarders, die heeft elk jaar zijn congressen. Maar dit jaar hebben we iets heel bijzonders. En dat is dat we daar gekoppeld hebben een heel bijzonder educatief programma, een studentenprogramma en al moonshots. Nou, wat is de Association of Space Explorers? In het begin van de ruimtevaart was het concurrentie. De Verenigde Staten, de Sovjet-Unie, wie was het eerste? Het was strijd. En het was de Koude Oorlog. Maar toen is ook al besloten, in 1975, om ook eens in de ruimte te gaan kijken of we konden samenwerken. De beroemde Apollo-Soyuz-missie kwam eraan. Een Russisch ruimteschip, een Sovjet-ruimteschip moet ik zeggen, Amerikaans ruimteschip, gekoppeld. En daar begon iets. We zeiden van, we hebben een prachtige planeet, daar moeten we voor zorgen. En er is al veel strijd en Koude Oorlog. Maar in de ruimte werken we allemaal voor die planeet van ons. We zijn allemaal, zeg maar, astronauten van ruimteschip Aarde. Hier zien we twee van de astronauten aan boord. Tom Stafford, Apollo 10 astronaut daarvoor. En Leonov. Leonov, de eerste ruimtewandelaar. En toen zijn die contacten gekomen. Die samenwerking tussen, zeg maar, de twee tegenstanders. En dat hebben we volgehouden. Rusty Schweickart, Apollo 9 astronaut. Testen de ruimtepakken voor de maan. Die is samen met Leonov en wat anderen zijn ze de Association of Space Explorers begonnen. Een vereniging van astronauten, ondertussen 400 in getal, zonder verbonden te zijn met een agency, ESA of NASA, zonder verbonden te zijn met een land. Het zijn individuen die allemaal minstens één baan om de aarde hebben beschreven. Met als visie de wereld van de ruimte gewoon te maken voor ons. Dat we de ruimte kunnen leven in de toekomst. En natuurlijk hebben we een doel. Het perspectief van die ruimtevaart gebruiken om de wereldwijde voordelen van ruimtevaart, daarom zijn jullie ook allemaal hier, we weten wat we al met ruimtevaart kunnen doen. Ruimtewetenschappen, de verkenning van het heelal en internationale samenwerking. Dat is heel belangrijk aspect hiervan. We doen het met z'n allen. En wat heel belangrijk wordt nu, daarvoor zijn we hier vandaag ook, om toekomstige generaties te informeren en inspireren en om een beter beheer van onze planeet te bevorderen. Ondertussen 400 mensen uit iets van 37, 38 landen. We komen jaarlijks bijeen op allerlei plekken. Houston, dit is in Toulouse bijvoorbeeld, allerlei verschillende plekken op de wereld. Astronauten uit een heleboel verschillende landen. En volgend jaar dus hier, in Nederland. Een prachtige plek om dat te gaan doen. Waarom? Nou, het is 20 jaar na mijn eerste vlucht. Er is altijd een of andere reden om het op een bepaalde plek te doen. Ik denk, dat is een mooie gelegenheid om het volgend jaar in Nederland te houden. Het is van 29 september tot en met 6 oktober. Dus een week lang komen er iets van 125 astronauten naar Nederland. Uit al die verschillende landen. Waar? Nou, hier op ESTEC, Noordwijk. We hebben Schiphol hier prachtig in het midden, want we hebben een culturele programma in Amsterdam, andere plekken. En we zitten natuurlijk hier in Noordwijk, daar zitten we, tussen Noordwijk en Katwijk, zitten we natuurlijk bij ESTEC. Daar hebben we de prachtige faciliteiten. Dus we krijgen al die astronauten voor de technische sessies, krijgen we hier op ESTEC. We praten elkaar bij. Dit is ook publiek toegankelijk. Er zal streaming zijn, zodat zeg maar iedereen die geïnteresseerd is in de ontwikkeling in de ruimtevaart, die kunnen dat gaan volgen. Dus dat is een van de aspecten die optreden. En we hebben een thema. Er is altijd een thema. En dit keer is het Generation Space, Shaping the Future Together. Dat is het motto. We gaan het met z'n allen doen. En daarvoor hebben we natuurlijk de jeugd nodig. De toekomst. De woensdag is altijd een community day bijvoorbeeld. Dan gaan de astronauten het hele land in. Naar universiteiten, naar scholen, naar bedrijven. Om de kennis te delen, om iedereen erbij te betrekken. Maar we willen dit keer al veel eerder beginnen. Namelijk nu. Nu, 8 oktober, beginnen we met moonshots. Met moonshots gaan we studententeams uitnodigen om te werken aan de crazy ideas. Gekke ideeën om die uit te werken. Een moonshot, net als naar de maan toe gaan. Binnen 8 jaar, na de toespraak van Kennedy, moest dat ineens gebeuren. Crazy idea, is wel gelukt. Dit is een opdracht van de Nederlandse Space Office, onze NSO. En financieel ondersteund door het ministerie van Onderwijs, Cultuur en Wetenschappen. We gaan dus heel veel jongeren enthousiasmeren. We willen 100 studententeams hebben, 17 plus, MBO, HBO, WO, het hele scala. In allerlei vakgebieden. Dus niet alleen techniek, niet alleen wetenschap, maar ook dingen als de medische kant, juridische kant en misschien wel hele andere ideeën. Allerlei verschillende disciplines. De moonshots beginnen eigenlijk vandaag mee. We willen zoveel mogelijk studenten enthousiasmeren. Er komen dit soort prachtige posters. Studenten uit alle categorieën, uit het hele land, willen we activeren. Er liggen al tickets, u heeft al dingen al kunnen zien liggen. 100 teams willen ze een beetje voor elkaar krijgen, voor die studenten-pioneers die met hun ideeën moeten komen. In verschillende categorieën. De aarde, dus de basis van alles. Biodiversity, geologie, klimaat. Dan komen er mensen. Allerlei verschillende aspecten van dat mensen doen. Psychologie, hairdressers, economie, al die andere aspecten. Daar kan je allemaal gekke ideeën in verzinnen. Toen kwam de techniek natuurlijk, alle technologie die nodig is. En tegenwoordig zitten we natuurlijk in het datatijdperk en artificiële intelligentie. En natuurlijk zijn er ook nog ideeën die er helemaal weer buiten vallen. Dus dat zijn de 5 categorieën die we gaan behandelen. Dus nu is het aan de studenten om binnen te komen. Het wordt een hele reis. Dit wordt de reis. Het ziet er ingewikkeld uit, dus we gaan even stap voor stap. Dit is het doel. Het congres, volgend jaar. Een week lang hier in Nederland. Dit zijn die onderwerpen, die 5 missies die we net noemden. Er zijn verschillende stappen om daar te komen voor al die studententeams. Een hele lange weg gaan we behandelen. 1 oktober, ja, eigenlijk nu en vandaag, sunrise. We zijn begonnen vandaag met de Open Day. Er komt straks een college tour, 11:15, voor de studenten. Om ze enthousiast te maken. Promotieteams komen eraan. Vervolgens zijn er verschillende activiteiten over het jaar heen. Ook hier bij de Space Expo in ESA Erasmus. Er komen steeds betere ideeën uit. Die concepten die gaan we uitwerken. En uiteindelijk willen we dat verbinden aan experts. Experts uit de industrie, van de agencies en ook experts van de astronauten. We willen astronauten koppelen aan die teams die dan ook af en toe contact hebben met die teams om dat te gaan doen. Ze gaan het voorstellen op de Industry Space Days. Als een soort, ja, dat is de eerste keer dat ze de ideeën naar voren kunnen brengen. En uiteindelijk, de beste, die gaan we op de grande finale op de open dag volgend jaar hier op ESTEC. Dan komt het op het congres natuurlijk, komt het naar voren. En die congres zullen we ook hier houden. Dit is Lucien, hij loopt hier ook rond. Hij organiseert alles. Fantastische klus. Ik vind het een heel mooi idee. En het moet allemaal in goede banen geleid worden door Lucien. En we zien er ontzettend naar uit wat we er allemaal gaan doen. Laten we even kijken, hebben we hier geluid bij? Het zou het mooiste zijn als we geluid hebben. En anders moet u het erbij verzinnen. Dan moeten we even naar het plaatje kijken. Dus vanaf nu, alle studententeams kunnen zich aanmelden om allerlei bizarre ideeën uit te gaan voeren. En kijken hoe je dat uitwerkt. Dat is het hele idee erachter. Dit is wel een leuke, misschien interessant. Dus de ideeën kunnen niet gek genoeg zijn om te kijken hoe je bepaalde problemen voor de planeet, voor de ruimte, al die verschillende aspecten kunnen we toepassen om dat te gaan oplossen. Dus bij deze alle studenten uitgenodigd om een prachtig idee naar voren te brengen. Dat is wat we gaan doen tot aan het congres. Wat doen we nou met de lagere scholen en de middelbare scholen? Want die moet je ook hebben. Je moet ze al vroeg enthousiasmeren. Daarvoor gaan we aan de slag op het congres zelf met vakkanjers. Samenwerking op allerlei technische gebieden, tussen de industrie en scholieren, om zoveel mogelijk jonge enthousiaste nieuwe ingenieurs en wetenschappers voor elkaar te krijgen. Dus dat is het tweede aspect en dat begint dus het jaar daarna. Dus dan gaan we op het congres gaan we daarmee beginnen, zodat we het hele scala van lagere school tot en met universitaire opleidingen, alles gaan we behandelen en alles gaan we in dit ruimtevaartjaar gaan we dat bespreken. Dus op deze manier beginnen we met vandaag de opening, zeg maar de eerste mogelijkheid voor de studenten om aan de slag te gaan. Het wordt een bijzonder jaar voor de studenten, maar ook voor de voorbereiding, omdat we volgend jaar hier prachtig in Noordwijk dat prachtige planetary congres hebben van de Association of Space Explorers. Hartelijk dank voor de aandacht. En ja, we hebben verschillende stakeholders die hier een rol bij spelen. En daar kunnen we nu tot overgaan. Dank u wel.
Thank you very much, André, for this wonderful news. And I almost regret not being a student myself anymore, because I would have some nice things to submit there. Today's students are the engineer, the scientists, and the technicians of tomorrow. So it's very important to capture that generation now to make sure we can make our future more safe, more sustainable, and make life on Earth better. How to engage this next generation, also a topic very dear to my heart, and why that's so important is something we're going to discuss with a panel of speakers in the next 25 minutes. And I'm going to call the speakers to the stage. We're going to try something, because I know you all want to give a lot of applause. So when I call a speaker, I'm just going to ask you to applaud for 3 seconds, and then I'm going to call the next speaker. So maybe we can try this. So when I say a name, you applaud for 3 seconds. Come on, don't be shy. Yes? Yeah. And then we stop. And then we can call the next speaker. And then at the end, we can all do a very big round of applause again. So I'm going to call to the stage as the first speaker, Mr. Josef Aschbacher, Director General of the European Space Agency. Yes. Mr. Dietmar Pils, Head of ESTEC. Mrs. Wendy Verkleij-Eimers, Mayor of Noordwijk. Mr. Harm van de Wetering, Director of the Netherlands Space Office. Ms. Kim Regnery, representative of the Space Generation Advisory Council. And Mr. Pedro de Hoek, former ESA astronaut, Spain's Minister of Science and Chairman of the European chapter of the ESA. Please have a seat. All right. So, Pedro, we will start with you.
Okay.
You were the first to learn about the Netherlands Moonshots 24 last week when you attended the Planetary Congress in Turkey. What do you think, or what does a moonshot mean for you personally?
Yes, for everybody who was there in Turkey, the 100 astronauts meeting together who will be here next year. For us, of course, moonshots is our thing. And it's a word that has been invented for a mission, and for a mission that inspires people. People want to do this, that opens new possibilities. So we are trying to do something that nobody did, and that requires a lot of effort. This is basically the thing that we call a moonshot or a mission. And it is now the center of gravity of all decisions that governments take, for example, for the economy. So in order for a country, for a region like Europe to thrive, we need that people have missions. And that is what really brings all the talents together. And the moonshot is just thinking about the mission to go to the moon, which is something that we have in mind. Almost everything else that opens a completely new area that requires a lot of effort and that inspires people because we want to do it and we want to be the one doing it, This is a moonshot.
So really thinking outside the box.
Really thinking outside the box and thinking of something that looks impossible.
Yes.
But if we put a lot of effort, it may be.
Okay, good. Wendy, you are the mayor of Noordwijk, the only municipality in the Netherlands with an alderman, een wethouder in het Nederlands, for the space sector. You were also one of the first to support the Planetary Congress in Noordwijk. Why is Noordwijk and you also so passionate about spaceflight?
Noordwijk has already an alliance for 60 years with the space. It's a very interesting place for space. And we have an alderman who's Mr. Roberto Tahark is very working hard with the province and also the government. And we're working together to make ESA ESTEC greater and interesting for young people, for the innovants, for we make also the space campus. We're working on it for the several years are coming also. And we are searching for the young, talented and curious people. And I think that's the way to having space here and to keep them space here. And so next year will be 60 years. It's a special year. And there we are very happy that the people, that the astronauts are also coming for.
So you're looking forward to host 100 astronauts here in Noordwijk?
Yes, we are very happy they're coming. And we invite them with our hands, with our love. And we got also a special program, and especially for the schools, for the children. André already told that. And not only that, but many people will visit us extra for meeting the astronauts also. And but not only that, also the hotels, the restaurants, the beaches, the shopping areas. All kind of people will be there for the astronauts.
Thank you. Dietmar, thank you very much for hosting us today here at ESTEC. You're the head of ESTEC and also director of tech. Talking about moonshots, so at ESTEC here we have thousands of people working every day on innovative challenges. Can you maybe name one that stands out for you personally?
That's a very difficult question, of course. So maybe first of all, as you said, ESTEC and tech in itself, it's actually almost a metaphor for inspiration and for innovation. So it's super difficult to really pinpoint one of the topics. Maybe just saying, having crazy ideas and trying to bring them to life is almost our daily business. So we foster this. There is several initiatives. We have a team which we call the Advanced Concept Teams, which brings together scientists from very, very different areas that come here, that work here. Of course, we're trying to bring the ideas of space into that, but they're very free and they're coming up with super exciting and innovative ideas. We have a program where we invite the entire space industry to bring us their ideas, and we support them with our engineers, with our experience, basically based only on the innovation. So we look at how innovative is this feasible at all, and then we support the team. So I think innovation, moonshots, what I saw right now, these 5 elements, craziness, is clearly an element that you will see here all over, and we see today in all of the exhibitions. So I don't want to give a specific one on this one. It would be not giving credit to all the other crazy and fantastic ideas that we're having here.
Yeah. So many moonshots at ESA and at ESTEC.
Yes, it's a whole moonshot universe.
Very good. Josef, one of the official tasks of the ESA astronauts, and we've gotten a new ESA astronaut class last year, is of course to do outreach, to involve the general public and also to inspire. As the Director General of ESA, who do you want to inspire most?
Well, that's a very important point, and I mean, these days when we talk about space, we see space globally is literally exploding. So much is happening in the United States, in China, but also in India. We have just seen India putting a rover on the south pole of the moon, which is a very big challenge, but also newer countries like the UAE and many others are really engaging in space. So as Director General of the European Space Agency, of course, I look outside and see what happens, but I would like to stimulate the European community, politicians, the general public, and make clear to them how important space is for daily life. And of course, it is the astronauts that are the most inspiring part, and I see here Pedro, we have just heard André, John McFall is in the room as well. It's fascinating to hear their stories. But space is also there for everyday life. It's Earth observation, it's weather forecast, it's telecommunications, it's navigation. It's so many disciplines we are serving. In other words, we couldn't have this lifestyle or this quality of life we have today without space. So space is absolutely essential. So if you say whom the astronaut should inspire, of course it is politicians. I'm having a very, I would say, an ambitious agenda put on the table for ESA, because we need to lift Europe in space in general. And that is not only European Space Agency, that is Europe as a community of industry, of entrepreneurs, of young people, creating new dreams and new inspirations. And we need really to lift at least one step, if not 2 steps further up. And this is a big challenge, you can imagine. And there, I can say the power of the new astronauts and the existing astronauts is enormous. And I think this is really something that, that is, for me, very important to utilize their star power, and I literally call it the way it is, for the communication that we need to do, because space is really there for everyone. We just mentioned one little figure, which maybe I should ask the question to the room. How much do you think every European, on average, is spending in space, collectively? If I ask you how many euros per year across the European population, what do you think how many euros are being spent? 4 million per head, per person. I wish. No, I can.
Great.
How much? Stella, yeah? Okay, 15,000? No, I can give you the figure. Every European, on average, today spends about 14 euros in space per year. That is very little. It's the price of a movie ticket, of a movie theater ticket. I can tell you, from the European Space Agency, we provide big movie, good movie for these 14 euros.
That's true.
But we have to increase it.
Yeah. Thank you. Harm, the Netherlands Space Office is also aware, of course, that the next generation is very important to contribute to space and the future of space. What is the importance, according to you and the NSO, for the space for society and what it means for our daily lives?
Right. Thank you. I think just as Joseph mentioned already a little, but so the human exploration is important because it brings countries together to work on common goals. That's unique, I think, from space. But on the other hand, by going in deep space and doing human exploration, you develop technologies, and the same technology or type of technology you can use to look the other way around. So to look at our planet Earth and to see what's going on with forestation or deforestation. How are the ocean temperatures developing? How's the climate developing? how's the ice masses developing, and even with satellites that are going daily around the world, you can see methane leaks that the day after you can stop. So it's really actionable data. So it's not only fascinating to go out there, it's also fascinating to look back, and that's also very important for our society.
Yeah, true. Kim, you're both a student and an ambassador for the Netherlands Moonshots program. Are you planning to participate yourself in the Moonshots Challenge? And if so, what do you want to propose? What category appeals most to you?
So I am indeed an ambassador, so I'm not entirely sure if I'm allowed to participate as well, but maybe I'll talk with Lucien after this. But I'm a biologist, so really fascinated with biodiversity in particular, and I think that there are so many new things to be still discovered around the Earth. There's so many little details that we still need to find out about. So I think that within the different categories that there are, I would personally love to participate in the Earth category. But I gotta say, the last category that we have, the extraordinary one, also sounds really interesting. I have no idea what I would exactly work on, but I'm sure that there are very out-of-the-box ideas that would be really cool to explore further and to learn more about. So
good. Yeah. Wendy, Noordwijk has the Space Walk of Fame. I don't know if everybody is aware of that, but it's basically a variation on the Walk of Fame, but then with some of the astronauts. You will have 100 astronauts coming to Noordwijk next week. Are you thinking to doing something special to maybe expand the Space Walk of Fame in Noordwijk?
Well, hopefully. We start with Wubbo Ockels in 2013. He was the first, he has the first tile with the boot of him. And André is also there on the Walk of Fame. But there are more, Italian, German, and some more from Europe. And hopefully there are coming more. It's a good alliance between Noordwijk and the space, and we hope that are coming more. And the walks, the whole walk is already sold out for a whole year this year. So the interest is very great of all kind of people from the Netherlands and above the Netherlands. So we hope there are coming more for after the week of space.
Good.
After the week of the astronauts.
It's a good reason to visit Noordwijk.
It is. You have to come.
Okay, good. Dietmar, this is probably the first time that we try to appeal students from a whole variety of levels. So really starting in primary school and going all the way up to university. Why is it so important to engage students also already from the early levels on? And how do you think that can impact them later in the future?
Yeah, that's a very simple answer. I mean, in all kinds of teams, when you try to be inspiring, creative, you try to bring in different people. I mean, and here bringing students, pupils from all kinds of ages together is creating a complete new frame of ideas. Because I mean, as you know, when the older you get, you have a certain tendency of really looking at whether it's real, whether you can actually make it, and if you bring in very young people, different ages, different also of course different disciplines from different science areas, different interests. We heard life science just before. Bringing this together, this is actually really creating the new ideas. And some of them are maybe super crazy, and of course some of them will not be happening afterwards. But if you don't think in that idea, and if you exclude particularly the younger ones, then I think you make a big mistake. So I think that's a great idea to have this really in these different ages. So I think that's really opening something.
Good. Thank you. My son is 4, so I can already try to push him a little bit to start thinking about the future as well. Pedro, we heard about collaboration, cooperation. You've been in space yourself, which of course is all about international cooperation. Can you tell us a little bit more about how you experienced that and why it's so important?
It is very important, as we have all said from Europe, and I'm sure our Director General has to stress all the time to all the countries. The cooperation of all the countries in Europe makes the project much greater than if only one country would be doing things by themselves. But on the theme of the space bus, I think that I would like to give it a different edge. Also here in ESTEC, or in the European Space Agency, there's another cooperation that is more important, I think. That is the cooperation between people that have different views on the world. So we have here, we get all of them in a small room, the scientist, the engineer, the physicist of a different discipline, people who are technicians who are able to fabricate the real thing. And a moonshot can only be done by all of these people pulling together, having the best solution from their point of view, and then joining together into achieving something that seemed impossible before the cooperation took place. So this is, I think this is the most important aspect of a mission or a moonshot. The aspect of having lots of several groups of enthusiastic people join together, each of them bring their own point of view on a problem, and all of them agreeing on a solution that would have never have sprung from one single group of like-minded people. And this is what we do in space all the time. Yeah. And that's how you break the frontiers. You are able to push the boundaries of the possible by cooperating between the most brilliant people on different disciplines.
Okay. Good, so basically all for space and space for all. That's the conclusion.
Okay, that's a good subject or a good theme.
Harm, the Congress and also the NL Moonshots will be sponsored by the Netherlands Space Office, also with funding from the Ministry of Education, Culture and Science and the Ministry of Economic Affairs and Climate. Why are you so keen to fund this? Why do you think it's important also for the Dutch citizens here?
Right. I think it's almost 2 years ago that André Kuipers came to us talking about his over 100 or around 100 astronauts coming to the Netherlands. So we thought this is a real unique event, so we must make something out of it. And all we know that one André Kuipers brings a lot of inspiration. So 100 times one astronaut really brings some inspiration. So I was also very enthusiastic about this moonshot approach to connect astronauts to groups of students. I think that will really be unique and work out very well. So, and normally I have to convince ministries to get some budget on certain topics for space, but this was an easy one. So the Ministry of Economic Affairs and Science, they were very happy to support this.
Very good. Kim, you're
maybe one thing to mention is, and Josef said it, so the space business is growing, so it's well, rapidly growing, and therefore you need your new brains and hands for the future already to be there. So programs like this will really help.
Yes. Kim, you will be an ambassador for the program. Do you think it will be hard to motivate people to submit, or you think it will be relatively easy because they're also eager to submit these crazy ideas?
I think that the way that that everybody is setting this moonshot initiative up is already making it really easy for people to participate and coming up with these crazy ideas. So everything that's extremely outside of the box is appreciated even. So I think that makes it more easy for people to form these teams and then come up with those ideas and actually participate. And also I think that indeed making sure that these astronauts are connected to these teams, that is something that in Dutch we would say it's spreekt tot de verbeelding, it's something that really makes it more special. It creates already this atmosphere around it of, oh, maybe more things are possible. So I think that in general that it will not be very hard for people to find friends to collaborate with and to make sure that a lot of teams apply for the Moonshots initiative.
Nice. Josef, you already mentioned it earlier, but spaceflight plays an essential role in our daily lives. You also talked about climate change, for example. I think many people don't actually have the idea of the extent what space does for our daily lives. What would be a doom scenario for you in case there would be no spaceflight anymore? What would that mean, you think?
Well, you cannot imagine if there would not be any space infrastructure or space flight or even space hardware working for a day. I mean, if you would switch off, say, all the satellites for a day, a lot of very bad things would happen, unfortunately. We see, I mean, for example, on On weather forecasts, 80% of our data come from space. So you may say, okay, if the weather forecast tomorrow is not good, that is not a big problem. But yes, it is, because a lot of our economy in Europe depends on weather forecast. It's connected one way or another to weather, agriculture, disaster management, forestry, ship routing, many things, not only climate change. It's really day-to-day life, which depends, for example, on weather forecast. Navigation, everyone knows perfectly well how important navigation signals are, of course, to come here, to drive, but also to fly. Trains are using navigation signals to safely organize the traffic. Telecommunications, so if you would switch off the telecom satellites for a day, many things would just collapse. Stock markets, for example, money transfers, all this need satellite infrastructure, not to mention entertainment and many other things that would just not work. But there's also many, many other things where space infrastructure is simply there every single day, every single life. Security, more and more becoming an issue. We hear it in Ukraine. The Ukrainian population or the fighters would not be capable of defending themselves without the help of space. Both for reconnaissance, to know what the situation is, for telecommunications, Starlink, of course, being a very important example. But it also shows that space is so strategic, it's so important for daily life that we need our European strength. And I'm not saying complete autonomy. I fully agree what Pedro was saying, that international cooperation will always be one of the pillars of space activities, but we need a strong European autonomy, more European autonomy as part of a wider international cooperation in order to really make sure that our living standard, your living standard of everyone, is guaranteed, and space is an essential means. Sometimes I say space is like the internet. 20 years ago, people thought about internet, you know, it's strange, maybe I need it, maybe I don't need it. Today, of course, nobody could live without. In 20 years from today, or already today, but in 20 years from today, even more, without space, you could not live. I'm very convinced that space is an infrastructure horizontally across all levels of society and economy, very essential, and that's why we need to invest and make sure that Europe is doing what it needs to be done to have its own strong capabilities.
Yes. So in short, without space and without space infrastructure, the world would come to a standstill. And I think what was announced today is a very good initiative to try and make young people also aware of that, and to try to make them enthusiastic about contributing to space. We are running out of time, but I would still like to leave a little bit of time to ask questions, to see if there's questions from the audience. Does anybody have a question for one of the speakers? André, if you want, you can maybe also join on the stage. Don't be shy. Yes.
Catch.
Hello, my name is Martijn Mulder. I'm a journalist for the Leids Dagblad. And I would like to know what if those ideas are developed and one or more has one at the final day. What will happen with those ideas after that?
The moonshots.
That's a very good question. Because, you know, 9 out of 10 ideas probably is a great idea, but doesn't go anywhere. But there's always ideas that make it. Crazy ideas. The world in which we live now is based on crazy ideas. Somebody who thought, well, let's have light of one frequency or something. Well, people said, what do you want to do with it? Laser light. Well, now we measure the distance to the moon. We do eye surgery with it, and you play discs with it. So the crazy ideas that come out of here, that there are some ideas in there, we don't know which one, that will be very important for our society. So, of course, these ideas will be picked up. We have experts already connected with the moonshots, with the ideas. So that will be developed, and well, I cannot tell you which one, but I'm sure there will be a great idea that will benefit us all.
Yeah. The box.
The students are developing it, and then, well, like you, after that, well, you've seen this is initiated, this is powered by the Netherlands Space Office and the ministries. So it's in their interest, of course, and if there are good ideas, they will pick it up and it will be continued. There will be a follow-up of it.
Yeah, maybe. Anybody else? In this area, there's an ESA Space Business Incubator Center. So every year we allow 10 new participants with great innovative ideas combined with space technology. And we try to help them together with ESA experts to bring on these developments. And yeah, we have really seen that some of those ideas in this SBIC, they become companies afterwards with a lot of success. So that's a possibility. So they can pitch their idea against all the others, and maybe they will be selected for the SBIC program.
Anybody else? Can I add something?
Sure, of course.
Okay. Maybe just from an ESA or from an ESTEC point of view, as said before, this is our nature to take these ideas and bring this to the next level. So if there are ideas that we feel that we have some industry supporting it, some governments and ourselves, we will definitely use our means to develop them further from a first phase. I mean, I've seen it. You want to go through a makerspace, which is maybe already some kind of a prototype. So bring it from there to the next level. Is if we see after a year that there is a chance of realism, or at least there is something that we really want to investigate, we will support this and will this bring into the right of streams that we anyway have established at ESA and ESTEC.
One last question from the audience. Yes.
What are some areas in astronomy or space technology you would like to see more innovation and like ideas from students? Like, what is a particular branch you would like to see more investment in?
Yeah. Maybe I start, but I'm sure there's a lot of people on this panel with good ideas. I mean, in astrophysics, astronomy, we have a lot of, I would say, breaking ideas and breaking technologies we're doing. Just behind you, you see Jupiter and the JUICE mission on the backstage there, which is looking for habitability of life out there. That means in the universe, in this case on the icy moons of Jupiter, which is fascinating and which is just incredible. And there we are, as you know, we are investigating this. Just imagine, and of course this is a bit of a longer term undertaking, just imagine that these satellites, the JUICE satellite, will confirm that life or conditions for life could be there. Of course, one of the next steps would be to go there and get a sample and see whether you can find traces of life. And just imagine you will find traces of life. What's their DNA? Do they have a similar one as we, or a very different one? I mean, this is just eye-opening. But there are also many other things. We talked of Hera before. Hera is having mini-satellites which are accompanying the Hera mission and measuring various characteristics of this asteroid. Again, something unimaginable, very much a breakthrough technology, but also in terms of inspiration, something that is quite fascinating, because you do look at an asteroid and see whether you can alter its path towards the Earth, if it comes towards the Earth through mechanical or other means of doing that. You see the James Webb Space Telescope on the other side of the room here. Again, there's so much science which will be discovered. Euclid, which has launched dark energy, dark matter. I mean, can you imagine that only 5% of our universe, everything we see and we hear, is measurable? We can see. All the other 95% is either dark energy, dark matter. At least that's what we believe, or scientists believe. So there's so many things to discover. So really the fantasy is wide open to propose elements that want to unearth some of these miracles and some of these discoveries which we have to make. But we have really many mechanisms to do so. The moonshot is fascinating and is really a wonderful idea. But even if it doesn't make the race, if the second or third or fourth place is still a wonderful idea, we have many opportunities in the Netherlands, in ESA, to bring them forward. A good idea will always succeed and end up somewhere.
Thank you.
Right, thank you very much. I think we come towards the end of the panel discussion. I would like to thank you all very much for your participation. Thank you, André, for the wonderful news you've given us. Thank you all very much for your attention. I wish you all a very great day at ESTEC today. Please explore, be curious, and get in touch with all the experts here. I'm sure you will enjoy that. For the people who have an interest in the science of Star Wars, please don't go too far. We will have a very nice panel at 11:45 with Jon Chase here also in the room. It's also very kids-friendly. Thank you very much, and please a warm round of applause for all our speakers.
Earth. It is my absolute pleasure to introduce the one, the only, Jon Chase.
Hello en goedemorgen. Hoe gaat het met jij? For anyone who doesn't speak Dutch, I said, hello, good morning. How you doing? My name's Jon Chase, and I'm a science rapper, an author of a few books, and a science communicator, which means I try to find ways to link science and the public together. And one way I do it is through things like this. This is the Science of Star Wars show, presented by me. Now, don't worry, you are in real good hands. I'm very trained in the art of presenting, as you can see. I've spent many years honing my skills to be able to do this here today. Now, if there are any problems, which I'm sure there won't be, you might see this slide. Look carefully. Okay, but I'm pretty sure we'll be fine. So there will be no Sith lurking around, although I think I saw some earlier. So, what are we here to talk about? We are here to talk about Star Wars. Who here has seen Star Wars? Yeah, okay. Now, who here has watched Ahsoka? Oh, a few of you. Don't worry if you haven't. Now, I've got to say that there might be a few spoilers in this show. So I apologize in advance. So if I go, like, say, do this, that means you might see something that you don't want to spoil your Star Wars viewing. Okay, so Star Wars, it's all about space. It's all about stars. It's all about the planets around those stars and the life forms that live on them and the technology they produce, the spaceships, the weapons, the vehicles. Now, I want to talk about some of the science that you could learn or find about or discuss when you watch Star Wars that you may not have realized it has. So let's start, well, at the beginning. A long time ago, in a galaxy far, far away. Here's your first bit of science. A galaxy far, far away. Have any of you ever stopped to think, how far might that galaxy be? How far, far away? And how long ago? Well, I did. Because I like this type of thing. And so I'm going to take you on a journey now into space. And we're going to start here on planet Earth. Look at this picture, a lovely city. It may be a few kilometers across. Quite a distance to walk or ride if you're here in the Netherlands. But what if you just kept on going all the way around the world? Well, you would then be going on a journey of 40,000 kilometers. Quite far, isn't it? 40,000 kilometers around the Earth. But how about if you wanted to go to the moon? Well, if you wanted to go to the moon, it wouldn't be 40,000 kilometers. It would be 10 times that distance, like walking around the Earth 10 times. It's 400,000 kilometers. Now, these numbers get a bit weird when you try and describe them because people are like, they're just big numbers. So let me put it this way. If you was in a rocket, it would take you about 3 days to get to the moon. So we'd say the moon is 3 days away at rocket speed. But let's speed it up a bit more. Let's go as fast as the fastest thing we know about, light. Light moves 300,000 kilometers in 1 second, which means it could go around the planet Earth 7.5 times in 1 second. That's quick, isn't it? Now, if you wanted to take that light beam from the moon to the Earth, that light beam would take just over 1 second. So we say the moon is just over 1 light second away. It takes light just over 1 second to get from the moon to us. What about the next, or the brightest thing in our sky? The sun, our nearest star. Well, the sun is just over 8 light minutes away. So it takes 8 minutes for light to get from the sun to us, which means if the sun exploded now, you wouldn't know for just over 8 minutes. You'd be sitting there, it's a lovely day, isn't it? The moon's just exploded. No, it's fine. There's a disturbance in the force. No, it's a lovely day. Yeah, wouldn't it be so nice, would it? So we say the sun is 8 light minutes away. But what about the next nearest star? Well, let me tell you guys. If you wanted to send a beam of light or even make a tweet to your friend at the next nearest star, Proxima Centauri, do you know how long your message would take to get there at the speed of light? 4 years. 4 years. So imagine you're being attacked by the stormtroopers, Darth Vader and all of them, right? And you're on your phone. And you're like, quick, ring Yoda. Yoda, we're being attacked. Send help. Yoda? It would take 4 years for the signal to get to him, and then 4 years for his signal to get back. So 8 years later, you'd get a message. Luke, hear you, I did. I did not hear you properly. Please send message again. This is the thing. Communication would be rubbish in the real world because it would take 8 years just to send a message and get it back to the nearest star. So Star Wars has to find a way over that. So they invent light speed and hyperspace. Now, I've just told you the next nearest star, but there's hundreds of billions of stars in our galaxy, right? More than 200 billion. Now, the thing is, they're spread out across the galaxy. And if you try to send a light beam from one side of the galaxy to the other, it would take 100,000 years. Just across our galaxy. So we say our galaxy is 100,000 light years across. But it's not the only thing out there, because we have other galaxies. Now, our next nearest galaxy, far, far away, is a galaxy called the Andromeda Galaxy. It takes light 2.5 million years to get from there to here. So the next nearest galaxy is 2.5 million light years away. Now, to get an idea of all the stuff that's out there, scientists thought they'd look at the darkest spot they could find in the sky using the Hubble Space Telescope. They looked at the darkest spot about the size of a tennis ball at 100 meters. And when they looked at that spot for 10 days straight, they noticed something. All these other little dots in the darkness of space. Those little dots are not stars, they are galaxies. In that image alone, they discovered about 5,500 galaxies. And when they added it up for the rest of the sky, they realized that there's probably about 200 billion galaxies out there. Each one of them filled with hundreds of billions of stars. So there's a lot of stuff out there. Now, these are real images of galaxies, some of them going back to near the beginning of the universe. Now, I said our nearest galaxy was 2.5 million light years away. That's our nearest spiral galaxy. The furthest one discovered is about 11 or 12,000 million light years away. 11 or 12 billion light years. You're like, wow, my head just melted. Don't worry, mine did as well, but it's going to melt a bit more. So, spoiler alert, close your eyes, cover your ears if you don't want to know this. Otherwise, please watch. Here's the galaxy of Star Wars. As you can see, there's many different planets and stars. These are stars with planets going around them, or star systems. You can see they're spread out across the galaxy, and the galaxy has these spiral arms. In the middle is this big thing called a deep core. Now, we know that pretty much all the spiral galaxies have a big, supermassive black hole in the middle of them, right? And at the center of galaxies, there's a lot more stars sending out dangerous beams of energy, right? Death rays from space. Yeah? If you're interested in death rays, check out a talk later today all about death rays from space. It'll be awesome, right? But living close to the center of the galaxy, you'd get loads of death rays. Wouldn't be nice for life. But yet still, the place where the human-looking people come from, Coruscant, is here in the center of the galaxy. But you can see all of these trade routes, the lines going out, and all these other star systems, like Mandalore, where the Mandalorian comes from, is the grey one at the top. The yellow one is Kashyyyk, where the Wookiees come from. But they don't talk, they just go, "Arr!" And then you've got Tatooine down here. You've got Naboo, and you've got Dagobah, where Yoda famously was. So this is the Star Wars galaxy, a spiral with a big core. Now, if you look at Star Wars, you may have thought there was only one galaxy, but we recently found out that there is another galaxy that they actually traveled to in the latest program, Ahsoka. So that means that Star Wars isn't just one galaxy, it is a universe filled with at least 2 galaxies and many more different objects you can see around, clusters of galaxies around. So it's very much like our own galaxy and universe. So where could Star Wars be happening? Well, let's start off with our galaxy. This is our galaxy, 100,000 light years wide. We're kind of over there where the arrow is, all right? If you look outside tonight, you might be able to see a big arrow pointing at you. Just like that. No, I'm joking, right? But if you zoom out from there, there's our Milky Way now in the middle. And there's the Andromeda Galaxy, 2.5 million light years between them. Let's zoom out some more. Let's see some more galaxies. That's our local galactic group. Now that group is just that little spot in the middle. And that's part of a wider area called the Virgo supercluster. These are all galaxies where Star Wars could be taking place. Let's zoom out some more. There's the Virgo supercluster in the middle. There is the local superclusters. These are all galaxies far, far away. Let's zoom out some more. The local superclusters are now that little area in the middle, and the rest of that stuff are all the galaxies in the observable universe, all the stuff that we can see, and there's stuff we can't see as well. To give you an idea, all of this stuff is made of matter, mass, and stuff, but this only makes up 5% of all the stuff that's out there. 95% of it is dark. The dark side. Now, it's dark matter and dark energy, but luckily for us, we've got clever scientists who are sending out missions to try and find out more about that stuff. The Euclid mission will go out and look at all the galaxies it can see within 10 billion light years, and it will be checking what the galaxies past, future, and present might be like and are in different places, and try to work out more about the structure of the hidden dark side of the universe. Yay! Now, of course, Star Wars would be rubbish if we didn't have star systems. So you don't just want stars, they're just big, hot things. You want somewhere to live, isn't it? A nice, cozy place to kind of do your washing and play PlayStation and things like that, right? Well, how many stars are out there in our galaxy? Now, here's a lovely image. Now, when you look into the sky, all of those stars are in our galaxy, but you can't see them all because some are really far and dim. But as you keep zooming in with a telescope, you keep seeing more and more stars. Now, you might be surprised that a guy called Carl Sagan suggested that there are more stars in the universe than there are grains of sand on every single beach on the whole of planet Earth. And then some scientists in Hawaii thought they'd try and check it out. And they made an estimate, and they said there's probably at least 10 stars for every grain of sand there is on the whole of planet Earth. Even more shocking than that we now know that pretty much every star in space, on average, has a planet around it. So it's not just stars, there are planets going around all of those stars. Now, things like Star Wars need planets in space, and they just say we travel from planet to planet through space. But science never knew if that was a fact until the 1990s, when scientists started discovering signs of actual planets around stars. We call them exoplanets. Now, no, not yet. There we go. Now, you might be surprised that these are actual representations of stars with their planets around them that have been detected. And to this date, there have been more than 5,500 confirmed exoplanets out there. Any of them could be planets where Star Wars could be happening. And this is just a few. And there are around they're around red stars, which are cooler. They're around slightly bluer stars, yellow stars, orange stars, all these different types of stars which have planets going around them. For reference, that's our sun at the top, the little lonely one in the middle, okay? And these are some stars bigger and some stars smaller. Now, the estimate is that of all these planets, about 40 billion of them are like planet Earth. So there's possibly about 40 billion places that's like planet Earth in size and in the right position where you could have water on the surface and possibly life. So when Star Wars came out, we didn't know this was a fact. Now we do know, since Star Wars, that actually there are planets going around other stars. But it gets even better. 80%, 8 out of 10 stars, are what's called red dwarfs. So if you looked outside, most of the stars you'll find actually have a red sun outside. But there is a planet in Star Wars that has 2 suns. Does anyone know the name of that star, that planet? Tatooine, that's right. I got a Tatooine the other day. My mum wasn't very happy. Anyway, right. Tatooine, it's got 2 stars. We call it a binary star system. Now, scientists thought, you'll never find a planet stable around a binary star system. It's not possible. And then they found one, okay? Now, just to point out, when you find a planet around a star, it has to be in a special place. Not too close, not too far, in a perfect zone called a habitable zone. Earth is right in the middle of ours, where water is liquid. It's not steam or it's not ice. It's perfect for making a cup of tea. We also found ones around exoplanets. We found habitable zones, and one around TRAPPIST-1 has 5 Earth-like planets, and 3 of them are in the habitable zone, so they could have water. But there's a problem. They're around a red dwarf. And when you're around a red dwarf, because it's cooler, you have to be closer to be in a habitable zone. And when something that size is close to their star, they tend to keep the same face looking at the star. So one side can get really hot, whilst the other side gets really cold. It's like our moon. Our moon always keeps the same face looking at us, and the other side is what's called the dark side. Not because it's dark, because it's the side we knew less about because we couldn't see it. And we say it's tidally locked. It always keeps the same face facing us. So 80% of the stars out there are red dwarfs and probably have planets that are tidally locked, meaning they keep the same face facing them. Okay, so here we go. Here's Tatooine. It's actually called Tatooine. Scientists discovered it, Kepler-16b with a Kepler Space Telescope, and they found that it has a planet going around a binary star system. If you was on that planet, you would see 2 suns rising in your sky. They nicknamed this planet Tatooine. But it doesn't stop there. Scientists also found a planet going around a distant brown dwarf. Brown dwarfs are cooler than red dwarfs and small as well. This is a really cold planet called Ogle 2061 Boggle. I think they fell asleep on a keyboard and naming it. No, all right? It's named for specific reasons, but they nicknamed it Hoth, like the icy world Hoth, although this is 1.5 times bigger than the mass of Earth. But if you went around Hoth, there's an asteroid field. Do you remember that one? Where they landed the Millennium Falcon. So we do have asteroids in an asteroid belt. We don't really call them fields. There is also other regions of asteroids, for example, Trojans that are in front and behind planets as they go around the sun. But they're not close together. They're pretty spread out. Now, the good news is you can have some that is big enough to fly over and land your spaceship on and fly into, like Vesta, 525 kilometers across. It's bigger than the Netherlands. So you've got a lot of space to land on it. But if you landed on it, there wouldn't be much gravity. So you wouldn't be walking on it like normal. Pretty much if you sneezed or even went, oops, you might just keep going. And then you have to wait a bit before you came back down. So life would be a bit weird on one of those places. Now, would you find one of these? Simple answer, no. That's called an exogorth. You would not find life on an asteroid. Not like this anyway. Okay, We also have the possibility of moons in space. Star Wars talks about moons where people live. There's the forest moon where the Ewoks live, called Endor, but there's many other moons. The Rebel base was on a moon, a forest moon. In Jeddah, in Rogue One, is a desert moon. And Kef Bir, where the Death Star was landed, and they had a big water ocean, that's a moon as well, an ocean moon. But on our Earth, on our solar system, we know of many moons. Planet Earth has quite a big moon, called the moon. But we have other moons that are bigger than our moon. Some of these moons are even bigger than planets. So we do have planet-sized moons. And some of them have great atmospheres around them. Titan even has an ocean, like the ocean moon. Although its ocean is mainly methane on the surface, but underneath there is a water ocean. So we might find places where life could exist on moons. Now, speaking of moons, there's another mission called JUICE. JUICE is a great name. It stands for Jupiter Icy Moons Explorer. This will be looking at some of the moons around Jupiter to check what the conditions are like there, because ultimately we'd like to see if life could exist on any of these moons. And if we did find that, who knows, maybe we'll discover exomoons around other planets. But from now, they're too small to actually detect. Okay, now this is not a moon. It's a space station called the Death Star. But there is a moon that looks just like the Death Star. It's called Mimas, and it's a moon around Saturn in our solar system. So we do have our own Death Star, but it is a moon, not a space station. Now, the Death Star would fit into that big gap on Mimas if it was there. Now, let's have a quick look at spacecraft. There's loads of spacecraft in Star Wars, lots of wonderful things we could see. Now, you might be shocked to know that our best spacecraft look nothing like that. We do have our own space station. Oh, no, sorry, that's not it. That's the Death Star. That's our Death Star. More like a life star or a lifeboat, okay? We've got our own thing that orbits, but the Death Star can travel through space, whereas ours can only go higher and lower in orbit. It can't go anywhere. Not only that, this lovely-looking space plane, the United States, I don't remember which shuttle this is. This is a shuttle that only went around the planet. It's an orbiter. It couldn't go to the moon. Now, all of these things to get into space need to be stuck on top of a rocket, and we've been doing that for 50 years. And they stick them on a rocket, they send them straight up. That sends out chemicals out the back to shoot it in the other direction. Now, if you wanted to get an idea of what that is, take a balloon, blow it up, let it go. Air rushes out one way, the balloon goes the other way, okay? Now, if you want to know what our best spaceship is, here it is. It might not look like anything special, but this is the thing that have actually got humans to land on another place, on the moon, and brought them back, all right? So this is the best thing we've come up with so far as humans. Not totally like space, like Star Wars, but, you know, we're getting there. And Elon Musk has developed this thing right out of the 1950s. It's the silver rocket ship, the big Falcon rocket. This is the one that they hope to take us to Mars and land on the surface. There's also ideas in the making like Skylon or even ESA's Space Rider. Now, quickly before we go, you may have seen around the place there is a TIE fighter, also known as the TIE fighter. Yeah? When they get upset, they take off their ties like whoosh, whoosh. I know it's a rubbish joke, isn't it? No, it stands for twin ion engine, right? Now, these things we see all across Star Wars with the bad guys. But the catch is that we do actually have this technology, but it doesn't work as you see it there. Now, you see them lift up and then start flying off. Now, here's the catch. This twin ion engine uses an ion thruster. Here is an example of ion propulsion. Here's a little machine called a lifter. Now, you might have wondered how something can lift off the ground and just float. Look at this. This is a real technology. He's got string just holding it down to keep it stable. He stuck 20,000 volts through it, and what happens is it's stripping electrons off of atoms, and it's creating what's called like positive and negative charge. Now, what it can do is it can send those ions, which are charged atoms that are slightly more positive in this situation, and may go flying downwards, and as they fly this way, just like the air being sent from a balloon, sending the balloon the other way, they get sent down, and they push it slightly up to cause it to float. Now, if you stuck that in another direction, you could stick it in a rocket. Or a satellite or a space probe. This probe uses ion propulsion. It is the Bepi Colombo mission, okay? We've had other missions that have used ion propulsion, but this one will shoot ions out the back to send it forward. Now, the catch is that it's not as powerful as a rocket. The ions come out really fast, but they only give the tiniest little force, like holding a piece of paper on your hand. That's how much it's pushing. But if you do it for a very long time, not like a quick few minutes, but if you do it for weeks and weeks and weeks, you can build up speed, getting to speeds approaching maybe 1/10 the speed of light. And using things like this, some people have predicted you'd be able to get to Mars in 1/10 of the time. Okay, so to finish up, we are going to race through this. Ability and training. If you want to be a Jedi, you need to train. But do we have Jedi amongst us? Well, astronauts have a lot of training and ability as well. They spend hours, weeks, months, and years training, grueling away to learn the skills they need to fly and survive in space. And it's not just people who are totally able-bodied. Even people with physical disabilities have been investigated by ESA to what are the effects on their bodies when they try to travel in space. John McCall, for example, has a prosthetic leg. And he's found that it normally works under gravity, but in zero gravity, it doesn't work as well. We need to understand these things to open up space for everybody, space for all. Now, physical disabilities, to fix them, you need to have some type of prosthetic, robotics prosthetics. And loads have been developed. Some even can be activated using signals from the brain. Not only that, there's even some that can detect the feeling back to the brain using those same signals, but in the other direction. Just like this guy. Does anyone know who that is? Anakin, that's right. On his way to become Darth Vader. That's right. Now, in the dark side, you can see the reason he needed this suit was to help him breathe, because he got burnt, he had his limbs chopped off. So he had all these replacement things to help him survive. I've got to watch what I say here. I've got to be very careful here. Very, very careful. Because the dark side is looming near everybody. Now, Darth Vader has this suit. And if you do anything mean, he might give you a chokehold. But this suit is made of technologies that we do actually have. And this is the type of spacesuits that we might hope to find one day. So his suit, it's got a mask that he can use to help him breathe in space. And you may not know that his suit can actually help him survive in space, as can the stormtroopers. Moreover than that, this suit keeps him alive. If you can get close enough to take it off, you could kill him. I didn't say that. I didn't mean it. Okay. So, just to say, without a spacesuit, you wouldn't survive in space. No one could. Okay, let's not go into that one. Princess Leia. Let's just skip forward past that. So to finish off, could you have Jedi abilities? Well, let me show you something. There is a real-life Jedi, right? So if you think about trying to deflect a light beam, right? Not a laser beam, a plasma beam, okay? Could you do that? Could your reactions be quick enough? Or look at baseball players. Baseball players have to react quicker than a signal can actually get from their eyes to their arms. They have to use instinct and training, just like a Jedi, just like an astronaut. But there is a man who can actually chop a bullet in half. His name is Isio Makai, and that's him hitting a ball bearing shot at him, and he's chopping it in half with a samurai sword. So do Jedis live amongst us? Potentially. It just takes a lot of training and a lot of effort. So my name has been Jon Chase. That has been a race through the science of Star Wars. I hope you've had an awesome learning experience, and I hope to perhaps see you all very much later. Thank you.
Wow. Wow. John, that was absolutely incredible. Thank you very much. I don't know about you, but I'm feeling really, really small after going through such a presentation. And I particularly like how, with the tidal lock of the moon, we end up flamenco dancing a little bit, don't we?
Yeah.
Oh, we can dance. We can do a flamenco dance.
If I was to do it like this.
Or that. But I'm told that your very serious escorts have arrived, so I think you better be heading off now. So put your hands together once again for the amazing Jon Chase. I hope they treat you kindly, Jon. So coming up after a short break, we have a presentation and panel about the Hera mission. Now, some of you may have already been over to the test center, where you can actually go and see the Hera spacecraft being tested and meet some of the team. So coming up right next will be Hera after a few minutes. humans of planet Earth. Please welcome to the stage Ian Carnelli and our Director General for a conversation about the Hera mission for defending Earth. So, Ian, tell us all about this exciting mission.
All right, and good morning, everybody. So it's my honor to be here with DG today. It's a very special open day for us because the Hera mission is en route for launch next year. So we take you through a little journey today. It's very short, but it starts 4.5 billion years ago in a galaxy far, far away. This is an image or a drawing of what the solar system, our solar system, might have looked like 4.5 billion years ago. So it was a nebula of gas rocks, and some of the gravity started to pull all this together. There are several models to describe how the solar system has formed. This is one of them, where basically the first gas planets formed. They migrated towards the sun. And in doing so, they compacted even further the rocks that were inside the solar system, forming the rocky planets. So Venus, Mercury, Venus, the Earth, and Mars. And the fact is that not all the material made it into a planet. So what was left over was asteroids. And asteroids, because of many reasons, mainly ended up being in a place called the asteroid belt, between Mars and Jupiter. Now, since there are a lot of dynamics in the solar system, these asteroids collided with one another, and their orbits started to change a lot. And some of them can come very close to the Earth. The history of the solar system is a history of collisions. So when you look at asteroids, and here you see an image on your right, and a simulation on the left. These rocks have collided, they've exploded, a lot of mess, really. And we know that because when we see asteroids from space missions, we see all these boulders and rocks, and we're interested to understand these dynamics. So these are some of the asteroids that have been visited by space missions. Some are colleagues from the Japanese Space Agency or from NASA. And you see that they're quite different in size. They can go from 1,000 kilometers in diameter for the biggest to very few meters for the small ones. And here you have an idea on the right. That's Itokawa with the space station. Gives you a little bit of a feeling what they are like. So I said that the orbits can be quite chaotic. And here you see some of them. There are hundreds of millions of asteroids in the solar system. And that's where we are, the little dot on the right. And as you see, sometimes these rocks come very close to the Earth, and sometimes they even collide with the Earth. I think the most famous collision was the one related to the dinosaurs. And of course, we don't want to end up with that. So when did we start as a space agency to look into planetary defense, meaning how can we defend our planet from such collisions? That was in 1994. When a comet that you see there broke in several pieces and then collided with Jupiter. And you see the black dots on the bottom right. Those are more or less the size of the Earth. And it was the first time that was seen live. As a result, Hollywood became quite excited about it. You might have seen Armageddon came out slightly after this collision. And we received a lot of calls from public saying, okay, I mean, we've seen this in TV. It has happened on Jupiter. What is ESA doing? So we started working on a planetary defense system. And here you see more recently, in 2013, an object about 15 meters re-entering the sky in Chelyabinsk in Siberia and exploding at about 20 kilometers altitude. It didn't impact the Earth, but the explosion was so strong that it shattered the windows and broke some buildings and injured about 5,000 people. So this is also a reminder that it's something we can do about, and probably the most famous impact crater is in the US, is the Meteor Crater. I invite you all to go and see it, and some other beautiful pictures of asteroid impacts with the Earth. So we know that that's happened, and we know that it's going to happen again. Of course, dinosaurs didn't have a space agency, and that's why we start working on it. So we don't make wishes, and today we make it a reality. So ESA has now a planetary defense system together with NASA. It's really a fantastic international collaboration that is based on 3 main pillars. The first one is to detect asteroids, so we have a network of telescopes. For those who are Italians, the first one is being built in Sicily to detect these imminent impactors, so the ones like in Chelyabinsk. We have a system that calculates impact probabilities. Is in the ESA site called Esrin near Rome. And every day we calculate the impact probability of all the objects we know. And we make sure that our calculations are correct by checking with the colleagues who run independent tests similar to us in the US at JPL. And then the final step is to deflect an asteroid, meaning to test the technology to change an asteroid orbit if we need to. Now, asteroid impacts are the only natural hazard that we can predict with telescopes, but we can also prevent by sending a mission to deflect it. And this is what Hera is about. So this is my last slide. Hera is an experiment that we invented together with NASA to send a number of spacecraft to a very particular object called Didymos, which is an asteroid that has a little moon orbiting around it, like the Earth and the moon. And the experiment is to change the orbit of the moon by a small amount, and this is what the NASA DART spacecraft did last year. You might have seen it in the news. If you haven't, I invite you to Google for NASA DART. You will see fantastic images. We changed the orbit by half an hour. The whole orbit is 11 hours, so now it's 10 and a half. But we don't know exactly why 10 and a half. Actually, our scientists predicted that it would have been 5 minutes. So that's where we're sending the Hera spacecraft that is built in Europe by ESA with industry. And it's actually a spacecraft with 2 small drones that will go there next year. Will take 2 years' journey to arrive and do some scientific measurement to understand exactly what has happened during the impact. Here you see some pictures from last year. So the scientists who have been working for 20 years on this experiment. So you can imagine there was quite an excitement. And on the top you see an image taken from a selfie camera during the impact. And you see all of this ejecta, all of this material that was released. The last few images on the left is the movie taken from on board the DART spacecraft. You see this is the real thing. You see the spacecraft that is targeting the moon with a Didymos asteroid that is slowly moving to the left and then impacting exactly in the center. It was an amazing engineering result, even better than we expected. And of course, the last image is low down so you can appreciate the surface. And given the amount of rocks, that's why we believe they are made by these type of collisions. And on the right, you see images of the impact as seen from ground with telescopes and this huge cloud of powder and rocks that were released. So this is our target. This is where we want to go. The moon will most likely look very, very different after the impact. And we have next week 200 scientists coming here to ESA to discuss all their modeling, all the scientific research to try to prepare for this very moment. This is how we measure the deflection by looking at the light pulsating before and after. And this is the network of telescopes on ground that has looked at this event. So it was really a planetary moment where scientists from all over the world were looking at the impact. Not only that, but also space-based telescope like James Webb that you see a model down there, and the Hubble, the famous Hubble Space Telescope. And they gave us these beautiful pictures with all these ejecta streams and trying to understand why these ejecta and how much. And probably this is my favorite image. This was taken 2 weeks after the impact, and you see the powder released during the impact, which is 10,000 kilometers long, and very inspiring pictures for us. So this is the Hera spacecraft. It's really a European project. There are 18 countries involved. And also JAXA. We have some representative of industry in the public, so feel free to ask questions. and it was a fantastic adventure to build the spacecraft in 3 years and launching it next year. So the satellite today is here in ESTEC. It's a very privileged moment. We are going to test it before launch, and I invite all of you to go to the test center, which is exactly on the opposite side of ESTEC, and you will see with your own eyes the probe that next year will be on a rocket and launched into space. Thank you very much.
Wow. Wow, what an absolutely amazing mission this is going to be. And you mentioned that it was a 3-year development time, but you also mentioned NASA DART, and obviously we've seen the videos from that, and there's been quite a lot of media coverage. Could you tell me a little bit more about the project's inception? How far in advance, up until the stage of development, did you have to plan for this?
So I started working on this mission when I was a YGT, which is a fantastic program in ESA for young graduates, those who finish university and can come here. And that was in 2005. So that's when we started to think, okay, how can we deflect an asteroid? At the time, the community was very small, and there were a lot of crazy ideas. Some of the ideas were painting asteroids in different colors to change the temperature so that they would go in a different trajectory, or attaching a net and towing the asteroids, or anchoring engines on the surface. So it was really exploring all kinds of different ways. It is only in 2010 when there was a scientist, Andrea Milani, from Pisa, who proposed a mission called Don Quixote, which was based exactly on this concept, to impact the asteroid at very high velocity, 6 kilometers per second, and change its trajectory, and then send a second probe to study what has happened. Then it took a few, let's say, years and a decade to get the funding, because it was something that it was new. There was no program in ESA at the time, so planetary defense is a fairly new program, and politics, of course, sometimes take quite a bit of time.
Yes, and I wanted to ask a little bit more about this international collaboration. Obviously, you have the NASA DART mission. How does it work? How do we speak to one another? And how do we drive the mission forward? Do we share data? Is that the end goal for the international science community?
Yes, so the data for this mission is going to be public from day one, which is also quite different from some science missions. And one of the difficulties was that the funding process on ESA side and the funding process on NASA side are quite different in terms of real process, but also timescales. So getting the two together was challenging. Was very challenging. But the fact that we're two independent missions also helped, because each mission had its own objectives, its own target, its own and so its own meaning by itself. And combining the two missions together, of course, you get the best result ever.
Yeah, absolutely. It's going to be a team effort.
Yeah.
And you mentioned the hundreds of scientists that are involved, and that's just on the European side. But for European scientists, it's really going to be a game changer to see the data coming this type of way. I wanted to ask you a little bit about the specific instruments that are going to be on this mission. Could you just briefly summarize what those instruments do?
Well, I would say maybe the most interesting instruments on Hera are something quite new for what we call deep space missions, so mission going into in the further solar system locations, which are CubeSats. CubeSats are these tiny spacecraft that were developed 15 years ago for educational purposes, but now thanks to miniaturization, innovation, they're becoming more and more powerful, more and more interesting, and we are the first mission to bring them in deep space. This is really new in this way to do planetary exploration. So when we get there, we will be releasing these CubeSats that are, you can imagine them as drones, who will be able to get very close to the surface of the asteroids and do incredible science. One of them carries a radar that is able to look inside the asteroid and understand its structure, if there are voids or if it's a monolithic rock. The other CubeSat will look into the mineralogical composition. Now, all of this was possible because we took advantage of developments and technologies that were done for decades for other missions, like Rosetta, that most of you know. We took so much from Rosetta. So we scavenged technologies, instruments from other missions, and we put them on Hera to go faster.
And it all sounds a little bit science fiction, but it is actually our scientific reality. And going forwards, I mean, the future is really bright for these sorts of space missions. And Josef, I don't know if you wanted to comment about what this type of mission means for future missions on the ESA side. Where do we see us going once this mission has flown?
No, thank you. I mean, you've just seen how impressive a mission like Hera is, and Hera is certainly, I would call it a new type of mission. It's somewhere a type of new space mission, as we call it sometimes, new space meaning a new way of how we put a mission together. As Ian was saying before, it took 3 years to come to up to the point today. In 1 year it will be launched, so at the end it will be 4 years between funding, conception, and really executing the mission. And this is typical of what happens today in many space disciplines, not only in planetary defense, but also in several other domains, in Earth observation, in telecom actually since some time, but also in exploration as a new domain where we are working more and more hand in hand with industry as a partner in order to develop a mission in a very short period of time. Of course, in this particular case, there's a firm deadline, because if we don't launch by October next year, then we cannot reach the asteroid, and then the mission would be useless, in other words. So there's a very hard deadline, and there's no choice other than to deliver the satellite to the launch pad and to launch on a certain day. But this is, although this is driven by the deadlines, but in general, we see more and more of this interaction in order to make it possible. So how the Hera team made it possible is because knowing that there's such a short time, you have to do everything in order to get there, meaning that you have to really, sometimes when there are compromises to be made, and in every satellite development or in every space infrastructure development, you have to make decisions. Do I want to go a bit deeper, have it a bit more accurate and a bit more precise, or do I accept a compromise and go forward, or maybe even change an instrument or some composition of the spacecraft? And this is very goal-oriented, as we call it, that you have a goal that means in 4 years you have to deliver, and therefore you have to be much more agile, much more dynamic, and much faster. And this is what I'm promoting. I'm not saying for all the satellites, because there will be satellites that need to be developed more in the traditional or classical way of really going very carefully through all the requirements, because so much precision is required. But there are other types of satellites coming more and more, what we call new space satellites or new space missions, where you give much more responsibility to industry. You work much more hand in hand with industry in a partnership, and therefore achieve, I would say, a quite impressive goal in a much shorter period of time, sometimes even with less financial resources. And this is exactly one example as we see it here in Hera. So I think this is a good example. I mean, if I may make one remark on Hera in particular, since the time is so tight, people and the team of Ian are really working day and night, weekends on this mission. Yesterday we had a small encounter with his family and friends of the project team. And it's just beautiful to see that they're coming here, they are part of it, they are suffering from it because you're not home and your colleagues are not home, but they're really part of it and they are contributing these missions. And this is really something that, as Director General of ESA, I have to say, is so beautiful to see that it's not only the project manager or his team, the one person that we hire in ESA who is working on it, there's a whole family working on it, and the friends are working on it. And I think this is beautiful to see that there's so much dedication and passion in space as we see it every single day, and this is wonderful.
It really is a Herculean effort, and it does feel like a family, everybody involved in the Hera mission, and also their families, because of course the team working on Hera are sacrificing themselves for meeting this really tight deadline. I just wanted to ask one more question before we take anything from the audience. do you have a, perhaps in hindsight, if you were to design Hera 2.0, was there one particular instrument that you didn't actually get on the mission, which you think, actually, you know what, that would have really, really been nice. Maybe the design didn't permit it, or there was just not the funding available. Is there anything that you would add?
Oh, yes. You know, the scientists are always pushing us to the limit. And as the Director General was saying, we had to do a lot of compromises and simplifications. For sure, there was something that the scientists always asked for, which was to land on the asteroid and then be able to transmit signals from the surface and pick it up from the other side. So it's what we call bistatic radar, so that the signal goes through the whole body and you measure it from the other side. This is something very, very challenging, and we've seen with Philae lander how difficult it is to land. So I cheated. I told them we would not do it because of cost and other reasons, but in the end, the propulsion system of the CubeSat was designed in a way that they could actually land if we were to do so. I just need to do a little bit of convincing to my ESOC colleagues, so our colleagues that will be flying, actually, the pilots of the Hera spacecraft, and I'm confident we will do it. So, but yes, next mission that we're inventing these days is a mission that is even more streamlined than Hera, taking everything we have learned and bringing it to the next level, which is what we call single string, so no redundancy, very, very challenging, but more instruments, and this is exactly the way.
Thank you both very much for an engaging discussion. This is an exciting mission. Again, you can go and see the real spacecraft. It's not a model. You can go over to our test center, and you can see it for real, and the team are also on hand to ask any questions you may have. So please put your hands together. And yes, thank you for a great discussion, Ian Carnelli and Josef Aschbacher. who was named. His name is Jon Mitchell, and Lonely Robot comes from the inspiration from a Mars mission. And if you imagine Mars, it's a very, very big place. And we've already sent robots to Mars. And just think, that's quite isolating. So imagine that you're a robot, and you're on your own, and you're a lonely robot. And the music will follow very shortly. To the stage, Jon Mitchell from Lonely Robot.
How are we all, okay? Just want to point out before we start, I can't rap, so that's out the picture. My name's Jon Mitchell. I started a band called Lonely Robot about 5 years ago, and I was very privileged to be asked to play at the inaugural Spacerocks event. in London. And I'm very privileged and proud to be back here on stage in front of you lovely people now. And this is a song called How Bright is the Sun.
Though it seems like madness cannot be before human intervention is metaphorical. The light in this salvation is dying of the same. The simplest solution is to end the game. And you can't hope to be there. How bright is the sun? The brightness is in leaving. We come too far from home to fall. How bright is the sun? A dying star in evening. You cannot hope to catch them all. Basking in the progress, blinded by the cost, and in the forward motion, we've never been so lost. When the sky is quiet, choked in satellites, only be a memory of how to put it right. You can't hope to be there. How bright is the sun? The blindness is in leaving. We come too far from home to fall. How bright is the sun? Dying star in evening. Cannot hope to catch them all. Catch them all. How bright is the sun? The blindness is in leaving. We come too far from home to fall. How bright is the sun? Dying star in evening. You cannot hope to catch them all. Catch them all. Catch them all. Thank you.
So I'm actually currently on tour with another band called Arena, and last night we were playing in Dortmund. So I finished in Dortmund, and I came here very quickly, rather like Phil Collins did at Live Aid, but on a much cheaper budget. And instead of Concorde, I used a Volkswagen Caddy. So it's nice to be here, albeit not in Concorde. This is a song which is largely about, I had a very strange dream a couple of years ago, well, quite a few years ago now, and it was a cross between Wall-E and The Martian. So if you can imagine a robot stuck in Mars, then this is what that's about. This is the song Lonely Robot.
Staring out at hazy red, some twinkle glitter firmament, celestial in bed. In distance only I can see this bright red dust so heavenly. You warm the deeper light, sad chiming nines in me. Please come home, lonely robot. Your heart is beautiful, programmed to receive. We miss you now, lonely robot. Your heart is beautiful. Why did we go to leave you far behind? A beacon in the wilderness, your memory reminds. Bone and parts depend upon a simple if repetitious song. Please come home, lonely robot. Your heart is beautiful, programmed to receive. Meets you now, lonely robot. Your heart is beautiful. These empty circles, terrestrial effigy. I came to find you, I simply had to see. Though much you are silent, rusty red decay, long forgotten relic, memory betrayed. Please come home, lonely robot. Your heart is beautiful, programmed to receive. We miss you now, please don't destroy the signal. This heart is beautiful.
Thank you very much. So my project is called Lonely Robot, which is the direct result of having an adverse reaction to being in bands. So I thought I'd come up with the idea of Lonely Robot, which is a strange thing because all the songs are kind of about disconnection and trying to find contact with human beings. So being in a band would be a sort of antithesis to that, or rather a solution to the problem. Anyway, this is a song all about that, and it's called Species in Transition.
Never make it. So I'm putting on this face just for show. I'll tell you in all honesty, it's a long way down and far below. Do you remember talking and just what that used to really mean? It doesn't seem nostalgic when the world is tearing at the seams. Oh, let go. You're just part of the condition. So goodbye to the species in transition. They said we'd never wake up, that we always choose eternal sleep. Where's the use for compromise when the water here is way too deep? We're waving and we're drowning. As a consequence, we rarely see when the broken record starts again, that it's all the same to you and me. Oh, let go. You're just part of the condition. So goodbye to the species in transition. Well, it kinda seems inevitable. Well, I call it faith for what it's worth. And when the candle finally dies, I will get up and walk off the earth. Oh, let go. You're just part of the condition. So goodbye to the species in transition. Transition. Transition.
Thank you very much. As As I said, the band is called Lonely Robot, and one of the concepts of the first album was the need for human beings to identify themselves on planet Earth and constantly looking away and trying to escape. And the song that exemplifies that is a song called Oubliette, which is recalls the pale blue dot, as mentioned by Carl Sagan. This is Oubliette. Dream that we forgot, wishing on the pale blue dot. Wait forever. I used to dream of deja vu. I used to stand as tall as you. I had a purpose through and through, but now forgotten. What is this place you call? Don't forget me. Just don't forget me. Oh, please don't forget me. Oh, as if the sun would never set, and I became some oubliette. Another day, I'm dusty red inside decay, the signal rust and disarray. I'm thinking of you. Do you recall or just forget this pretty world and Oubliette? And I will meet my architect, and he will take me. What is this place you call? Don't forget me. Just don't forget me. Oh, please don't forget me. Oh, as if the sun would never set, and I became some oubliette. What is this place you call home? What is this place you call home? Don't forget me. Oh, please don't forget me. Oh, just don't forget me. As if the sun would never set, and I became some oubliette. Don't forget me. Oh, just don't forget me. Oh, just don't forget me. Oh, as if the sun would never set, and we became some oubliettes. My name's Jon Mitchell. Thank you very much for listening. Thank you.
1, 2, 1, 2. Oh, big round of applause. That was beautiful. And Jon Mitchell and Lonely Robot. We'll be back in 10 minutes with world-renowned author ALASTAIR Reynolds.
SpaceRocks, and welcome to our next panel on science versus science fiction. It's my pleasure to introduce you two very wonderful speakers. We have ALASTAIR Reynolds, a former space scientist who once also worked here at ESTEC, but who turned away from studying pulsars and binary stars, and who is now a leading sci-fi writer with 19 novels and more than 70 short stories under his belt. And we also have our own ESA, Mark McGowan, our ESA Senior Advisor for Science and Exploration. Please give them a very warm welcome.
Righty-ho, I think we have to take a seat and talk about the interface between science and science fiction. The European Space Agency, of course, here, in some ways, turned science fiction into science reality. But ALASTAIR was here doing that, and then he decided to go the other way and left. When exactly was it, ALASTAIR?
Well, I started here in 91, the end of 91, so I came here on November the 18th. So I remember it was a really cold November. Real sort of shock to the system coming to the Netherlands on a sort of cold, wintry.
But you'd done your PhD in St Andrews. I mean, come on, how can it get much colder than
well,
that?
Well, that's what I thought, yeah. Yeah. But yeah, I'd come straight from Scotland and then sort of stayed here till I left in 94 and went to the University of Utrecht for 2 years to do a postdoctoral position. And then I came back to ESA as a contractor, and then I was here till about 2004.
Yeah, so that was before I was here. So I know you from having read your books and your short stories, and then I arrived here and they said, well, ALASTAIR, you know, he used to work right here. So there's some people actually still at ESTEC today who do know ALASTAIR from when he was here. And tell us what you were doing at that point and what you're interested, because it's very relevant to what we're doing today in science.
I'd come off a background in observational astronomy at St Andrews, so it was like real old school, looking through telescopes, studying the night sky. And the focus of my PhD work was binary stars, where you have a star much like the sun, maybe a bit heavier, and then the other thing could be a black hole or a neutron star. And it was like, the question was, how heavy is the compact object, the neutron star? So my PhD work was on looking at that from an optical perspective. When I came to ESA, it sort of shifted more into looking at X-ray data. So my first job was, 50% of the time was to look after the ExoSat archive, which was a database that contained all the data from an ESA satellite that had orbited between 1983 and 1986. So it had been and gone before I joined, but it was still quite a fresh mission, and it was still the best set of X-ray data that was available to the community. So my job was to service the community by making that data available. So looking after the archive, making magnetic tapes, sending it out to astronomers around the world. But I had 50% of my time was then free for me to exploit the database. And there was also other sort of archival astronomical data in that database. So I was free to sort of dig around in there and find some science that maybe hadn't been exploited.
Right. So this is something that's very important to us today. We fly these space missions, and the data are obtained either in a survey, where you say we're going to cover the whole sky, and then you can use the data, or they might be pointed observations, where somebody like ALASTAIR or one of our astronomers out in the community says, no, I need to point at this object and take this particular kind of data. So this is a very complicated plot here, but it'll probably disappear off the screen in a minute. But give us a bit of an idea what these pulses here then of emission are at the bottom.
Well, this was one of these types of system where you have a solar-like star, actually called a BE star, and then something else orbiting it. And often scientists weren't sure what the period of the object was. They might see some X-ray flashes, so the pulses would be every now and again you get an X-ray flash that might give you an idea about the rotation period of the compact object. But then working out what its orbital motion around the other star was could be a lot trickier. And you'd have to sort of use a combination of optical and X-ray data and try and sort of synthesize the data sets to figure out what the orbital period was. Because it was only when you knew that you could really get a handle on the mass. And the mass feeds into general relativity, the really detailed models we have about how matter behaves when it's under extreme pressures and temperatures. So it's a really good test for how well we understand extreme physics in the universe.
And it sounds, in a way, like much of what we do, a bit like a detective story in a sense, right? You have some observation, you see something happening, and you say, what do I understand about this situation? Can I add more data to it? And it strikes me, to sort of bring it to obviously the topic for today, is that that's how you plot a short story or a novel, is that you have a thing. There might be a beginning, or maybe it isn't, right? I mean, how do you go about plotting a full novel? I mean, it's daunting to anybody. I mean, some people in the room may have written books, but every time I think about it, I think, how do you get into the beginning of that and find that thing and then build a story out from there?
I always feel a novel is such a huge commitment in terms of the number of words you have to write that if you think about it too hard, you just wouldn't bother. So it's like a journey of 1,000 steps. You know, you just do a little bit each day, and then somehow you get to a novel. But I'm not one of the. There are many writers who, broadly speaking, they say writers fall into two camps. There are architects and gardeners. The architects are the ones who spend a year thinking about the structure of a novel, the detailed plot. Agatha Christie was an architect because she wouldn't write a murder mystery until she'd considered every possible ramification of the story, the tiniest detail. There could not be a single loophole in the story because it had to be absolutely watertight or it wouldn't work as a murder mystery. So she was very much an architect. The other types of gardeners, they're people who just start writing, see where the story takes you, and often you take a lot of wrong turns and the story will surprise you as the writer because it'll take you in directions you weren't maybe anticipating. But for me, that's the way I do it. So I certainly don't approach it very sort of schematically.
But there must be something which triggers you in the first place. I mean, one of your books, which when I had read it before and when I came here, it struck me you were here at the time where one of our space missions was planned. The story is Pushing Ice, and it struck me, this is the Rosetta mission in some sense, right? This is going to a comet and harvesting and getting water. And then, of course, it just goes bananas. I mean, unfortunately, Rosetta didn't go quite as far as they went in Pushing Ice. I recommend, I mean, it's one of those wonderful books which you read where you think you're on a fairly quotidian story, kind of, here we are in the solar system, we're going here, we're going to dig up, and then it just goes batshit crazy in the best possible way. So, but I mean, I'm not asking you if that was the inspiration, but there must be things in your day-to-day life where you say, that's a thing.
Yes, prior to Pushing Ice, I'd written 3 or 4 novels that looked at the question of life in the universe from a certain standpoint. That's one of the sort of big drivers for me as a writer, is to think about the possibility of life in the universe. Is there anybody else out there? If there's nobody else out there, that's interesting. If there is somebody else out there, that's also interesting. So there's really no downsides to that. But there's so many different sort of approaches you can take to the question. And I'd taken one particular approach in the Revelation Space books, which were the first books I'd written. But for Pushing Ice, I wanted to look at it from a different perspective. And I think if those of you who are sort of fans of Star Trek, Star Wars, you think in Star Trek, the humans meet the Klingons and the Romulans and the Ferengi. And in Star Trek, we have Star Wars. There's lots of different sort of galactic cultures that are meeting at a sort of roughly the same technological capability, so they can have space battles. But if you think about the time scale for the evolution of life in the universe, it plays out across billions of years. That's how galaxies form and planets form and stars form. It's a really enormous time frame. So the likelihood of any two cultures meeting at any kind of parity in terms of their social and technological development is quite slim. It's much more likely that if there is intelligent life out there, it's probably been out there a lot longer than we've been around. So we're not going to have an awful lot in common. But I wanted to find a way of telling a science fiction story in which there was that parity. So the sort of motor behind Pushing Ice is to come up with a scenario where you can have different galactic cultures meeting on more or less common ground.
Yeah. I mean, one thing which is a big feature of your books as well is this idea about, in a way, alien archaeology, going out and finding mysterious, weird stuff that's just lying there, sort of detritus lying around, and having people monetize it as much as be curious about it. I mean, you know, typical humans, right? We'll go somewhere and we'll see the Parthenon, and it's, oh, how can I sell that? How can I make money out of that? Which, of course, you know, is a very human thing to do in a bad way. But also, it always strikes me that this is a real problem that science fiction has, is sometimes, as you say, setting out the enormous time scales, but also setting out the enormous scale of things. And one thing that features a lot in your books is enormous alien artifacts at a scale which are incomprehensible. And so some of your work has been filmed, and when that happens, do you feel that they've captured the scale, the sense of grandeur that you had in your mind? Because in a book, I have to make that up. I'm the reader. I have to see that, and you guide me through that. But in a film, it's right there. It's on the screen.
And in films, I've had a couple of adaptations done that were very short films. The longest of them was 15 minutes. And you can't pack the whole of creation into 15 minutes, so they have to leave a lot out. I think there are things that you can do on the page in a narrative form that you can't easily do in the visual media. And I think that's why, for me, science fiction as a written form is still interesting, and it still excites me as a writer. It's because you can really begin to evoke those scales, time scales, dimensional scales, in a way that's quite difficult to do in the visual media. And so also, I find it's still got utility for me as a writer.
Completely. I mean, and I think, you know, I hope everybody here in the audience is a reader and have kids who are readers. And I was talking to my wife earlier on today and to our kids, you know, when I was young, when we were young, we're roughly the same age, you know, books were kind of the entry to another world. Textbooks, science books, culture books, but science fiction as well. And today, I mean, so how do you feel about that? I mean, you said it still has relevance, but most of the big streaming channels are quite addicted to science fiction as a trope, but does that remove from the written word?
I've always felt, for me, there's a certain part of my brain that only lights up when I'm reading science fiction. And the visual media, they can do wonderful things, it can be exciting, but they don't quite scratch that particular itch. And I think I can't be alone in that. So you can have as much proliferation of streaming channels and and science fiction content as you like, and a lot of it I enjoy, but it doesn't take away from the special sauce that you get from written science fiction. So I'm never worried about that. I mean, I think if there's a lot of science fiction out there for people to consume, it's a win-win.
Yeah.
But at the end of the day, people always seem to find their way to the fiction. You know, they'll see, for instance, they'll watch the Netflix adaptation. So Zima Blue was one of my stories that was done for Netflix. And they did a very nice job on it in 15 minutes, but they had to leave a lot of the thematic depth out of the story because you just have to. But people who liked the movie then sought out the short story and they found something else in it, you know, other layers that were there. So it's all good.
Yeah, I mean, we spoke to the two writers, Dania Abraham and Ty Frank, who are James S.A. Corey, the authors of The Expanse. And I don't, you know, I hope that it happens that way, or it went the other way, that people were readers because the books were written first. But the provocative question, I don't know if you actually have time to read when you're writing, but which books in the last few years do you wish you had written?
Oh, so many. I've just written.
You've just written.
This summer I read a very, very good book, which I think is either coming out or it's due out in the next sort of few weeks, and it's by the writer Naomi Alderman, and she did a book a few years ago called The Power, which they made a TV show out of. I think it's probably still airing, but she's done a very, very good recent novel called The Future, and it's sort of about where we are in the world with big tech, globalization, social media, all the things that are going wrong, but she's sort of saying, how could we fix this in a good way? What could we actually do to improve our lives, to get rid of misinformation, fake news, over-commercialization of everything? And I found it a very, very provocative book. It's science fiction, but it's sort of science fiction 5 years in the future. So I very much enjoyed that.
And your Poseidon's Children series, of course, starts close to home, then goes out. I particularly still love the idea, because if you have the chance today to go to our Mars yard and see our robots there, I love the fact that on Mars, humans are not allowed. The robots have taken over Mars, and they cannibalize any piece of technology that comes to the surface. So don't go there in a spaceship. You will be eaten very quickly by the robots who own Mars. So Mr. Musk, watch out, is all I can say. But there's that as well. There's that's a very optimistic series. It's got, of course, twists and turns and dark stuff. How do you think about the world? Because it's very easy to write dystopian science fiction today, possibly trivially easy. We live in a dystopian world, one could argue.
I'd been, around about the time that I started thinking about that sequence of books, I'd obviously had a wonderful time working at ESA, and I'd always been stimulated by all the activity and sort of thinking that goes on here. But I was just as blown away when I visited the Kennedy Space Center for the first time. And it was coming around was like coming up to the 50th anniversary of the Apollo moon landing. Sorry, the 40th anniversary. So this was only 2009, around about then. Long time ago for those of you who are young. But at the time, there was an awful lot of excitement and sort of a sense of optimism in the air about where America was going to go next. And there was all sorts of talk about going back to the moon maybe by 2019, so a date that's already in our past. But I was fired up by that, and I started to think, I'd really like to write a broadly optimistic science fiction series that starts with us on Earth and then sort of explores the journey that we take as a civilization out into the solar system and then maybe beyond. And initially I was going to, the whole thing was going to play out over 11,000 years. It was going to be this ridiculously ambitious, multi-generational family saga. And I wrote the first one, which is set 200 years in the future. And I thought, now I've got to skip 10,000 years for the next one. And it was just too hard, I couldn't do it. So I reined in, it doesn't span 11,000 years, it spans maybe 500 or 1,000 years.
And yet we have House of Suns here. I mean, that's another book which has this sort of long duration family that spans many generations. So that's something which features. It's constantly probing and trying to set out that the universe isn't just happening in a room in one day. And like, a Star Trek series, I don't mean to trivialize at all, but sometimes for television, you need to tell it quickly to get it over. It's got to happen all in 24 hours or a few years. But you're at that position now where you've written so many books and they sell so well. At least I hope they do. I mean,
me too.
I'm not sure about the clothes. I mean, I expected him to turn out in Gucci. No, he's a scientist. Once you're a scientist, you're always a scientist. But you've also been able to indulge yourself, I think, in a brilliant way. I mean, space pirates. Why space pirates? I mean, why not, I suppose?
It was too much fun not to do. And I have, people who know me know they take the fun out of me mercilessly for this, but my PC that I actually use for all my day-to-day writing was actually bought when I was still working at ESA. So it's over 20 years old now. It's a Dell PC, so very good computers, Dell. So you can take it from me. But whenever I have an idea, I'll create a file on the hard drive. It might be an idea that I don't revisit for 10 years. And that was one of those ideas. I had the germ of an idea about a kind of realistic way that I could do space pirates with solar sails. And of course, solar sailing, using the pressure of sunlight to navigate around the solar system, is something it's real science. It's something that we're beginning to experiment with and deploy in real space activities. So I thought, the idea of spaceships with huge sails on them, like old pirate ships, isn't totally ludicrous. So I could have a lot of fun with that, with the rigging and shoot the rigging with cannonballs and things like that. So it was just one of those fun ideas that I kept revisiting in my head, thinking, I'd love to do that one day. And then eventually the time came where I had the right sort of window in my writing that I could have a go at that.
And you've done detective stories in space, kind of crime procedurals, which everybody understands the genre. You kind of figure it out, but then you add your layer to it. But it also begs the question, because you're a scientist, is there a point where you actually look at what you do and say, you know what, I don't care anymore. I'm just going to write Star Wars. I mean, don't get me wrong, it's brilliant, but it's fantasy. It's not science or science fiction in the kind of hard way. Or do you feel constrained by that sometimes? I'm a scientist, I have to kind of get things right.
Well, I love science, and I love it if I can find a way to match a narrative to science. But whenever I've read an article in a magazine, some nice little scientific discovery or conundrum, whenever I've tried to wrap a story around that, it's maybe not worked as well as when I've just had a story idea out of the blue. So the best way for me to work, I think, is just I'll have an itch I've got to scratch in terms of a story, and I'll write that story, and some science will sort of enter it naturally in the process. My sort of mantra for myself is the story has to be paramount. If I have to bend the science a little bit for the sake of a good story, I will. Breaking science outright is a trickier one, and I do it occasionally. I mean, the classic example, if you're writing science fiction, is do you allow yourself faster than light travel? Because Einstein told us 120 years ago that it's probably a big no-no We don't really have a way to understand how you could travel faster than light in the universe, or signal faster than light. But of course, if you allow that constraint, it takes out all sorts of stories. You can't, I love, in Star Wars, I love the fact that Luke Skywalker can get in his X-Wing, and 6 hours later, he's crashed on Yoda's planet. He's met Yoda, rather than 6,000 years later, which it would take if those of you who saw Jon Chase's brilliant talk about the science of Star Wars will know how far apart the planets are in the Star Wars universe. So it would take thousands and thousands of years to tell even the most rudimentary story arc in Star Wars. And who would stick around for that? No one would. So you've got to have hyperspace to tell that kind of story.
So in that regard, I mean, something that's sort of been a thing I thought about a lot is that with Jules Verne and H.G. Wells, we effectively made science fiction reality by going to Mars, by going to the moon. There's this idea that some people still carry, that anything that you dream up could be true. And I just wonder to what extent we're at that limit with general relativity, with light speed, with other things. We're actually drawing a line around the human species and say, actually, it's very unlikely we'll ever do that. Do you feel a responsibility, I feel as a scientist a little bit, as a science fiction writer, to say, actually, your horizons are maybe not as broad as you might wish they would be? Because wishful thinking is a real problem in a society that's trying to cope with major problems. Oh, climate change. Oh, we'll just invent some tech and it'll go away, because it happens in science fiction. Is there a sense where you say, no, I will not go beyond this line because now I'm going to give the wrong impression?
Well, I try and signpost to the reader when we're in the realm of real science versus when we're in the realm of completely made up bogus science. Sometimes there's a little bit of a hinterland between the two, where you sort of edge into speculative science, which might be correct, might not be. But things like, it's highly unlikely that there's any way of traveling faster than light. So if your sort of future beliefs are predicated on that you think we'll get out of the mess we're in by building a hyperdrive, then you're in trouble, because it's probably not possible. But I'm not dogmatic about it. I try and allow a sort of 5% reasonable doubt about these things. Maybe our understanding of physics will be turned on its head in the next century, and we'll find that things we think are definitely impossible now might turn out to be possible. So I'm not absolutely black and white about these things. But I do think, as a writer, I try and broadly indicate to the reader, this is within the realm of the possible. This is definitely not possible.
Yeah.
But you can take things to absurd lengths. So referring back to the trilogy, the Poseidon's Children trilogy, one of the sort of themes that emerges in that book is I'd been reading about the ultimate fate of the universe, and it's quite dispiriting when you read about it, because we think about, well, one day the sun is going to fizzle out, but okay, but we could still move somewhere else in the galaxy, and so that's okay. But if you look on a timescale of billions and billions of years beyond that, then matter itself eventually sort of evaporates, and there's nothing left. There's no energy differences anywhere in the universe. There's just sort of little black holes floating around, and everything's sort of slowly cooling. And then that might not even be the worst thing that happens, because maybe space-time sort of collapses, and everything gets erased. And you think, well, every sort of deed that we do, every great work of art is destined to be erased at some point in the future. That's quite a sobering thought for a sort of Sunday morning, isn't it?
And if you talk to particle physicists, they say this may already have happened.
Yeah.
That space-time may actually be unraveling right now, and it's traveling towards us at the speed of light. So we're dead. Yeah. Well, on that note, what I'd like to do, because Alistair, what you have done is broaden my mind with your books and cause me to think about, where I place the science that I do in the bigger picture. Because science fiction is also, it's a way of reflecting on who we are as human beings. It's a thought experiment which says, let's imagine X, Y, and Z and put a human in the middle and see how they react. And I think it's a really important thing that we do. It's not just entertainment, it's not just wishful thinking, it's just not fantasy at all. It puts humans in strange positions. And for that, what I'd like to do, if I may, is ask Jon to come on stage, because what we're going to do today is present Alistair with the first SpaceRocks Inspiration Award for having inspired us and hopefully generations of future readers. I do recommend you go And
Thank
get
you.
Alistair's books. Amazing
Oh,
stuff.
Thank you. Thank you so much.
Michael.
Thank you. Thank you.
You're welcome.
That's wonderful. Thank you. Because of my connection to ESA, it means the world for me to be back here, and I'm really grateful for SpaceRocks for making that happen. It's been such a joy to have an association with SpaceRocks over the years, and it's wonderful. Thank you.
Thank you very much.
I don't deserve it.
No,
I accept it gratefully anyway.
Absolutely, you do, and we expect that you will come, and as we take SpaceRocks back out into the wild again, some events outside of ESA around Europe. Alistair, you're very welcome to come with us.
She'll hate me for doing this, but a big shout out to my wife, because she's been behind my writing for 30 years. Go on, put your hand up. So none of it would have happened without my wife.
Well, thank you very much for coming, everybody. We'll be back on in a few minutes, I think, with the next session. Thank you very much, Alistair. It's a great pleasure.
Thank you, everyone. Thank you.
Scientists on the stage. First of all, we have André Kuipers. He's an astronomer and an ESA project signed for the gamma ray observatory called Integral. He will start with a short presentation on gamma rays and space radiation in general. Then we'll have Nicol Caplin, astrobiologist and our exploration scientist in the Human and Robotic Exploration Directorate. And I will also be here. I will be moderating the conversation, but I'm also discipline lead for life sciences in the HRE Directorate. So please, Erik, Nicol, welcome to the stage. Please give a warm round of applause. Yes.
Okay, good afternoon. Yes, I'm André Kuipers, and I look at everything out of space regarding X-rays, gamma rays. Who wants to go to space? Yeah, I bet after this session you don't want to go into space anymore. And also when I came into the room, it says space rocks, bringing space down to Earth. And maybe I should not have been invited because I bring stuff outside space onto Earth. Yeah. But luckily we have an atmosphere around our own Earth, which inhibits radiation from gamma rays, X-rays, infrared. And we can see things in space because those rays, they penetrate through the atmosphere, like the visible and infrared. And also you can see a couple of satellites up there which investigate those rays from space. Well, the nearest Death Star close to us is the Sun, and I will tell you why. At the left part, you see a picture we can all see. It's in the optical, and you see also a little bit of sunspots there. At the right, it's in X-rays, and it's really a little bit more devastating than the optical picture. But when the Sun becomes active, you see these flares going off the Sun, and they're not only, the Sun is not only emitting X-rays and gamma rays, but it also shoots charged particles into space. The X-rays, gamma rays, they arrive about 8 minutes at Earth, but the charged particles take a couple of days to arrive at the Earth. And when they arrive at the Earth, when you have charged particles, you get currents. You get electric fields. So when the particles encounter a satellite, they can distort the satellite. And if you want to navigate around ESTEC with your phone, you will not be able to use it anymore because these GPS satellites, they have been, they have been destroyed. Well, not destroyed, but they have been, the currents affect the satellites. And if it's stronger, they can also infect sort of the ionosphere, which is part of the atmosphere. And then it can affect the ozone layer, for example. And if the ozone layer gets thinner, you get sunburned because of the UV radiation of the Sun. But there are far more dangerous things out there in space. Gamma ray burst, for example. Gamma ray burst, they emit in 1 second as the Sun does in its whole lifetime. So that is more devastating than our little Death Star, the Sun. And here I show you what a gamma ray burst is. A star implodes or gets into a neutron star, but when it's not only imploding, but it also shoots out a lot of material outside in a cone of radiation. And then it also interacts with the surrounding medium. Then you see this thing. But it's not, so it's doing its thing, and it's shooting radiation outside into space. But imagine if it's oriented towards you, all these gamma rays and X-rays, they will affect you. So this is an image of the whole sky, just projected in a kind of way. And in a couple of, and I will show you a movie that these gamma ray bursts, they happen all over the sky. They come from all over the place. And so it's not, and the bar you see in the middle is our Milky Way, and you see that they happen not only in the Milky Way, but everywhere else. And these gamma ray bursts, they happen more or less once per day, at least. The brightest gamma ray burst seen so far happened last year. You may have not noticed, or you could have noticed if you read the papers. That was called the brightest gamma ray burst of all time. The brightest of all time, the boat. So the boat in Dutch as well. So here I show you a picture. So at the left part, you see how many gamma rays were seen per second. So you see these small, sort of smallish ones at the left. These were the brightest seen before October. And in the middle, you see the huge flare going on. Up to about 7 million gamma rays per second were seen. So imagine what happens if this gamma rays, if this cone of radiation is pointed towards you. I looked it up, 9th of October 2023, the ISS was nicely going around the Earth. And at that time, there were 11 astronauts on board. And one of them was Samantha Cristofioretti. So imagine what happens. Well, she was still doing her things over there and happy, and all the astronauts were doing their work. But they could do it. I mean, they didn't notice it because this gamma ray burst was something like 2.4 billion years or light years away, so very, very far into the universe. And this was the brightest. So what if a gamma ray burst hits Earth? I mean, not one which was 2.4 billion years, light years away, but if it's in our galaxy, for example, what happens to the Earth? I will show you a little movie about what could happen.
Some scientists believe that 440 million years ago, Earth was hit by a gamma ray burst, or GRB, a deadly beam of radiation that devastated life on the planet.
See, if it happens nearby, all those rays are concentrated onto the Earth. It destroys the ozone layer, and a lot of chemical reactions go on, and they might trigger a new ice age, for example, or distinguish life on Earth. So you should be happy, because you are traveling on the safest spacecraft there is in the universe, and that is Earth. Remember that when you go home. But beware, if you want to go on holiday somewhere next time, you should be aware that there are these death rays in space. So if you go to the ISS, you will be irradiated by X-rays and gamma rays. If you go to the moon, the same thing will happen, because the moon doesn't have an atmosphere to protect you. If you want to go to Mars, it's the same thing. And even if you want to go on a holiday somewhere in a nice location in space, there is radiation. So I think it's the best to stay on Earth, because that one keeps us safe. Thank you.
Thank you, Erik.
Yeah.
You made me a little bit scared, I have to say now. Nicol, you're an astrobiologist. You examine what happens to life when we go outside of the Earth. Can you talk a little bit about some living organisms that actually don't care so much about all of this?
Yeah, absolutely. I mean, Erik very correctly said that human beings are vulnerable and sensitive. So if we were exposed to the space environment, we wouldn't do very well. But that's not the case for some organisms that you find on this planet. They are organisms that can exist in the extremes, and we call them extremophiles. Some of you may already be familiar with them. There are different kinds of extremophiles, some that can live in very warm environments, some in extremely cold temperatures. You can even find these, and when I'm talking about extremophiles, I'm not talking about large mammals like us. I'm talking about really microscopic life. So even deep into the Antarctic crust, you can find some really interesting fungi and also bacteria. But what is particularly interesting for spaceflight, and I talk about this in a human exploration context, is that the biggest showstopper to going further, to going and exploring the moon and beyond, Mars, and maybe in the far future, other destinations, as Eric quite rightly said, it's the radiation factor. That is the #1 showstopper. And there are some organisms that we found on this planet that can actually handle radiation far, far greater than you or me. And some of these can be found in deserts and basins and even in your garden. Who here has heard of a tardigrade, for example? I see a lot of hands going up. And if you're here in SpaceRocks, you're probably familiar with sci-fi as well. And if you're a Trekkie, and I can see a couple of you out there, there's also a Star Trek storyline which focuses on the tardigrade. This isn't the only organism that is able to resist this kind of thing. There are others. But what we can do is perform experiments on them. We can send them, and we regularly do this. We have sent them historically to the International Space Station. We've put them inside to look at the effects that microgravity has on them, and we can bolt them to the outside of the space station, and we can expose them to the entire suite of space stressors. So this isn't just the radiation, but this is a combination with complete solar radiation, extreme temperatures, and even space vacuum. And what we found, quite famously, is that these organisms, tardigrades being probably the poster organism for surviving space extremes, is that they do survive this. But the crucial thing and a common misconception is that they don't survive these for a very long duration of time because it is a specific type of radiation that seems to get them in the end. But the very fact that some of these organisms can survive space leads us to think that, okay, when we're pointing our telescopes and our spacecrafts deep beyond where we are, this is the sort of life that we're going to be looking for first, because it's the most resistant life as we know it.
Thank you. And yeah, I mean, of course, my interest as a human physiology researcher is also, what with humans? I mean, Erik already said, probably best not to go into space, but I mean, we're going to explore, we're going to go back to the moon, we're going to go eventually onto Mars. So, what with humans? What steps do you think we should take to make sure that we understand or at least map that environment as good as possible to try and make sure we can send humans in the end?
Well, that's why we are here at ESA. We have to build satellites to investigate the radiation around the Earth. We also look at the Earth, but we also look into space. So you look at what happens if something happens somewhere out there, what the influence is on the Earth. And we also, on the ground, we can do a lot of experiments to see what is happening. Mm-hmm. But we also look at, for example, in our solar system, for example, if a sun goes flaring, where does it go to? How does it interact with other planets and moons?
Yeah. Okay.
So, like JUICE, for example, the satellite is at the back.
Yeah.
That is going to investigate the icy moons on Jupiter. I'd like to see if the sun shows a great big flare, how is it influencing these moons, for example?
Yeah. So what you say basically is also first trying to understand that environment better, generally
Yes,
speaking, and then of course try to translate that to what that could mean for living organisms and for humans. Okay.
No, if you go somewhere, you have to check out how do I go, what do I have to wear. I mean, as an astronaut, you have to wear a lot of things, but you have to also go into your spacecraft, your container, and it should be protected against all these death radiation.
Yeah. Nicole, you talked about some living organism extremophiles that we have investigated on ISS, outside ISS. Now, of course, our team in particular is also preparing for going back to the moon. Can you talk a little bit about what type of research would be very interesting to do there and how that could then relate eventually to human exploration?
So, of course, we've already sent these extremophile organisms to the ISS, but as Eric said, that's very close to the Earth, and that's actually still within the magnetosphere. So you're still protected by quite a lot of the, from a lot of these galactic cosmic rays and so on and so forth, and heavy ions and protons. But by going further, so we're going to the moon, and there's a very exciting project coming up called the Gateway, and that's a spacecraft that will be in lunar orbit. We could do same again. We can actually expose these organisms to the lunar environment, which doesn't have this protective layer, and we can really get an impression of what true deep space radiation effects are.
Yeah, exactly. So that's something that indeed the team that Nicole and I work in, that's something that we are currently trying to prepare just to make sure that we can get that additional understanding, because in the end we want to send humans there, we want to send them for a longer period of time, so we really need to understand the environment and try to translate what that could mean also for humans. Now, okay, we talked already about why it's actually not a good idea to go there. We talked maybe already a little bit about what type of research we can do to better understand it. Can you maybe say a little bit more about the types of things that we can do to try and counteract it? So let's say we're going to do it anyway. So what can we do to try and make it as good as possible or as safe as possible for human beings to venture into space?
That's a very good question. Yeah.
So one of the first things would be spacecraft design. So designing spacecraft in mind for having these solar events, the flares and such, and thinking about the thickness, the shielding of the spacecraft itself. But another thing that we could potentially do is getting into the realm of sci-fi again, but not quite. So, for example, we study another organism similar to tardigrades and also available in your back garden, and they're called rotifers. And rotifers are really interesting scientifically because you can subject them to vast levels of radiation. And then they can repair the damage to their DNA themselves. And this mechanism isn't quite fully understood, but we're sending them to space. And this is really exciting because if you can use something like this as a model for DNA damage repair, then you can infer that up to what it means for humans, and potentially use whatever secrets rotifers are holding for humans, for benefiting exploration further out into the cosmos.
Yeah, Nicole, you mentioned shielding as one of the things we could do. I assume that's also, I mean, this is less my experience, but I assume that's also something you need to do when you send spacecraft, satellites into
I mean,
space.
even just satellites without humans or spacecraft without humans, they need protection. I mean, the instruments are so delicate. If there is a current, you throw a current in there, basically, charged particles, you're gone. So you need to protect your satellites as well, and not only the humans.
Yeah.
I mean, protecting the humans, that's a step higher. I mean, you really probably need thick shields of metal, because that can absorb X-rays. But gamma rays, it's a little bit more difficult. They go through everywhere.
Mm.
I mean, we have a very thick atmosphere, and we should be lucky for that, because that captures most of the X-rays and gamma rays, but it's harsh over there, yeah.
Now, I've seen sci-fi, fiction episodes where people are living on Mars, but they live underground. Is that something you think we might be going towards? in the end?
They live underground.
Yeah, they live underground.
Yeah, no, that's maybe one of the reasons. Yeah. Also the UV radiation from the sun. I mean, it's not only X-rays, gamma rays, but also the UV radiation. You don't want to get sunburned or these things. Yes, that's one of the options to go down under. Yeah.
And this is also a potential theory for life on Earth. So there's a theory called panspermia, and that was the belief that life was imported here from somewhere else in the cosmos. And you're laughing, you're laughing, but it's a plausible theory, because if you think about the tardigrades that survive exposure to open space, the one thing that got them, in our experience, was the UVC, so it's very, very specific type of radiation. If you can imagine that a tardigrade was perhaps buried in some layers on an asteroid or an icy comet or something, and in the early formation of the Earth, when Earth was bombarded, these landed here, that is one possibility for how life actually emerged. And that is a question that's been since the dawn of astrobiology, and also just the dawn of mankind, and wondering, where is it that we came from? It's still, an open question.
Okay, I never heard that theory, but okay.
We should talk more.
Yeah, good to know. One thing we actually also have investigated at ESA, and it links also to the radiation and some of the countermeasures, and it definitely links with sci-fi as well, is hibernation. So we have done actually a CDF study here, concurrent design facility study, where we wanted to investigate the plausibility or how realistic it would be to hibernate humans on a mission to Mars, because it could have potential beneficial effects for bone and muscle deconditioning. It could have potential effects for radiation. And also psychologically, it could help a little bit. Nicole, do you want to say a little bit more about that?
Yeah, I can speak a little bit more about that. And you might be dipping again into the realm of science fiction. But in actual fact, it's not totally far away from what we do. If you think about in the medical settings, you can, if somebody is undergoing trauma and needs a surgery, you can induce a coma. You can dramatically reduce their metabolism into a steady state. And if you employ this similar method, we could use that as a way of preserving astronauts for going further out into space. And if you think about the mission duration, say, for instance, you want to go to Mars, well, this is about a year. We're looking about a year to get there at the closest orbit. To get an astronaut from the Earth to Mars is going to require an awful, awful lot of resources. Even the International Space Station, which is crewed all year round, and it has been continuously for the past 20 years, there's a lot of resupply missions, and we send food up there constantly, and there's all of the waste that generates. But if you could make an astronaut go into hibernation, reduce the metabolism, that would in turn reduce the resources needed, and then you wouldn't have to send so much, because every single kilogram that you send to space really counts.
Yeah, thank you. Yeah, maybe to add to that is that we have indeed done a study, and we also work with some accelerator facilities here in Europe on ground, where we can do some space radiation focused research. So we can do some biology research or some material sciences to see how certain materials react to that particular environment. One study that we have done together with scientists in Darmstadt in Germany was to look at mammals, rats basically, who naturally don't hibernate, but they were induced in torpor. So torpor is indeed a state of lower metabolism, basically what, for example, bears go through their winter sleep. So they put these rats in torpor, and they've seen that when they put the beams on them, so when they irradiated them, that they actually had a bigger protection mechanism against it. So they were less sensitive to damage coming from the radiation. I think it was roughly 1/3 less sensitive. So in that sense, it's also interesting. Of course, if we can ever translate that to humans, that would be quite cool, because then we could hibernate humans, but I'm not sure how crew would feel necessarily about that.
Might be a bit stiff when they wake up.
Yeah, probably. Yeah. And I think, psychologically it could also help, because as Nicole said, it's roughly 8 to 1 year, 8 months to 1 year going to Mars. but it's also really boring because, you know, there's nothing to do while you're en route, you're in transit. So, of course, the real work starts when you land on Mars. But
you just have a good sleep. Yeah.
Yeah, yeah, true. But yeah, you could maybe take away some of the psychological stress from that as well. Erik, you mentioned you shown this very apocalyptic video, you know, of one of these gamma ray bursts, you know, hitting the Earth, and it could bring us in an ice age. That's when you scared me a little bit. But like on a day-to-day basis, like for example, while we're sitting here, is there anything that is happening to us because of this?
Well, not really. No, I would say. I mean, gamma rays bursts. Some gamma rays are strong, like this one. You see effects, little effects on Earth, like. So when you have a strong gamma ray burst, and the gamma ray radiation goes into the atmosphere, especially the ozone layer, it breaks oxygen and nitrogen, because gamma ray radiation is so energetic, it can break apart molecules. And when you get when you break up oxygen, it can react with carbon, and then you can get carbon oxide, which is like smog we have on Earth. And when you have smog, you don't get much of the sun rays anymore, and that has an effect on everything on Earth, basically. For example, they found you can investigate tree rings, and if the sun was shining nice, you get big rings. When there was not much sun, you get small rings. And they discovered that about 400 billion years ago, there was such a huge event which had more effect on Earth, and I think it also affected some of the living species in the water. So you see things happening on Earth, but not in your daily life.
Okay,
except when you have a strong solar flare, it can affect GPS signals.
Okay.
It can affect the radio signals.
Okay.
That's where you see it, but not.
I would say, because I'm a radiobiologist by training, and my favorite thing about radiation, people say, oh, it's really, really dangerous. I said, yes, it can be dangerous, but radiation is so easy to detect. And if you have the right instruments, you really pick them up. I remember being in the lab, and I would use, some of you might know what a Geiger counter is. It's the thing that goes, it has a very, very specific, I find it quite a relaxing sound when it's at a tick, 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 tick. And I was in the lab one day, and all of a sudden, this Geiger counter that's on the side just went mad. It just exploded with this noise for a couple of seconds, and then it fell. And then I realized, it's detected solar activity. Yeah, it's just something that's really special.
Yeah, a human body is still sort of well adapted to this kind of cosmic radiation. It's just on a low level, so to speak.
Okay.
We're not protected against the big disasters. But,
okay. Yeah, I actually have a question on that last thing. You see now some of these conspiracy theories that everything is giving radiation, like AirPods, that it's not, safe.
Different kind of radiation. I mean.
It didn't happen to me.
I mean, ionizing radiation. Erik showed that spectrum. You had the electromagnetic spectrum, and the highest energy with the shortest wavelengths. They are the danger zone, if you like. They're the very aggressive particles that can cause real damage. But in our day-to-day life, everything emits radiation. You and I emit radiation, and if you put a Geiger counter over a banana, for example, bananas are quite radioactive, but you would need to eat, I think about 4,000 bananas to start feeling any kind of effects. But everything that is produced is produced with safe limits in mind, and with the specific type of radiation. Also in mind.
Good. Thank you very much. It seems like space radiation is something that we haven't fully figured out, especially on how to put humans into space. But we're going to explore from ESA's side. We keep on exploring and we keep doing the science to try and keep our astronauts as safe as possible. I would like to thank the speakers, Nicol Caplin, Erik Kuipers. Thank you very much for being here. Please a warm round of applause. Thank you very much.
Thank you.
And stay around because the next panel we're talking about some of our ESA missions, so that will for sure also be interesting in 15 minutes. See you soon. Thank you.
series of mission updates for you. The first of which is a very special mission called JUICE. And I want you to give a warm welcome to the stage to Olivier.
Great, thank you very much. I'm very happy to be here and to present the status of the JUICE mission. I'm the lucky JUICE project scientist, lucky because it's just a fantastic mission. Before I start with an explanation of what we are doing with this project, I got many questions about how JUICE is doing because we launched in April, so JUICE is doing fine. We started the cruise phase a few months ago. We have still 8 years to go, so we have a more quiet phase, I have to say, and that was good because this year was very, very intense. I will start with this moment, which happened on the 14th of April 2023.
Allumage de EAP, décollage.
That was probably the most intense moment of the project for this year and over the entire project lifetime, because you know it's the most critical moment of a space mission to be launched in space. We are quite lucky with all the preparation with Ariane Espace. We had 1 day of delay due to lightnings, but other than that, the launch was just perfect. And the perfect injection, together with the launch in the middle of our launch window, has the consequence that we are more fuel on board, so we can even have a better science return for the mission. A quick slide to show the overall timeline, because another question I got, besides the fact that how JUICE is doing, is that JUICE is launched, so what are you going to do next? It's like for many people, the project is over. And in fact, no, with the JUICE launch on the 14th of April in 2023, we are just in the middle of the project. Everything started in 2007 with the call for mission. Then there was a tough competition, selection, instrument selection, and so on. It lasted eight years. And we started the project with the industry in 2015. So you see already from 2007 to 2014, there were already 8 years of selection and study phase. Then 8 years of development with the instrument team, the project, and the industrial consortium. And then the launch in April. And then we start a new phase, another 8-year block, what we call the cruise phase, because it takes 8 years to go to Jupiter. JUICE is very heavy. We cannot send it directly to Jupiter, so 8 years to go there. We need to be patient. 2031 is the arrival date. And then there will be, for many people, the most exciting phase of the project, from 2035, 31 to 2035, 36, 37, depending on the mission is going. That will be the harvest, and when we get all the result of JUICE. So as you can see from this view graph, we are in the middle of the project, and it's a 30-year project. So why are we doing that? JUICE means Jupiter Icy Moon Explorer, and we are interested in the icy moons of Jupiter, which on this view graph are Europa, Ganymede, and Callisto. So from left to right, it's the distance from Jupiter. So Io is the closest to Jupiter, and Callisto is much further away. And we are mainly interested in the 3 icy moons, which possess inside, underneath the surface, more liquid water than on Earth. It's a fascinating thing to think that underneath the surface of those 3 icy moons, there is more water than on Earth. And since liquid water is an ingredient for life, so where there is liquid water, there could be life. So it's very important to explore those worlds and to understand better where is this liquid water, how much, and so on, to better understand the possibility for life in those moons. So you see Io, Europa, Ganymede, and Callisto. The other aspect which is interesting is they are all different, and it's very interesting when you explore the solar system to explore different worlds. For example, if you are interested in activity, you have to go closer to Jupiter because of the gravity of Jupiter, so it's more Io with the volcanic activity, Europa with the geysers and the ice tectonics. And then you have less active world at Ganymede, and Callisto is probably a dead world. If you are interested in oceans, it's Europa and Ganymede. Callisto with a question mark. If you are interested in the origin of this system, you have to look at Callisto, because Callisto has not changed over 4 billion years. So the image of Callisto now is the same 4 billion years ago, while the image of Europa now is the image 50 million years ago. And the image of Io, it's 1 day late because of volcanic eruption every day. So it's very interesting to understand all these 3 different moons, and in particular to see where the oceans are located, and to build on the next mission about possible search for life at Europa, Ganymede, but it will not be for JUICE, this one. We are not going to study the moons in isolation, because we are very interested by the moons, but also with Jupiter, because there is a lot of interaction between the moons and Jupiter. And one illustration of this interaction are the aurorae, because as you can see on this image, there are the aurorae on the north pole of Jupiter, imaged by the Hubble Space Telescope. And part of this aurorae are triggered by the moons themselves. So part of the light that you see on this image are the aurorae due to the moons. So there is an invisible link between the moons and Jupiter. And to understand whether there is life on this moon, whether the moons are habitable, we need to understand also the relationship between the moons and the giant planet. But we are not doing only planetary science, but because Jupiter and all these moons form a miniaturized solar system, it's very important to understand those worlds to better understand all the exoplanet system that we discover every day. So we do not only do planetary science, but also exoplanetary science with JUICE, so it's a very exciting mission. This is how the spacecraft look like. So it's a big spacecraft, 6 tons at launch, huge solar panels. The bigger solar panel used in a planetary mission. You see the shape of the solar panel, very special shape. We need this big solar panel because we are far from the sun. You see the body of the spacecraft with a large GAN antenna to communicate with the Earth. You see a lot of booms, appendages. There are a lot of antennas on JUICE because we are going to make a lot of investigations with the radar, antennas, booms, to measure electric field, magnetic field, to probe the subsurface of the ice of the icy moons. So it's a very complicated spacecraft in terms of design and deployment. Here it's an image of the big solar panels that were taken in Airbus in Leiden, in fact 10 kilometers from here. And you see the size of the people near to the solar array to see the size, to understand the size of the solar array. So it's a very big solar array, 85 square meters. We need that to power only 1,000 watts at Jupiter, so it's less than a vacuum cleaner at home to operate the spacecraft and all the instruments. And on the left, you see the complex sequence of the deployment, which could never be tested on ground due to the size of this system. Another image of the spacecraft taken in Germany 2 years ago during the development phase. And here is to show that in the middle, there is a black part, which is called the vault. And because there is a harsh radiation environment at Jupiter, it's very bad for the electronics, for the systems to operate at Jupiter because of the radiation environment. And we have some cavity to protect all the sensitive electronics inside the JUICE, to make sure that JUICE will survive not only 1 month, but a few years around Jupiter. Another image taken in the test center here at ESTEC, to test the thermal design of the spacecraft. That was done 1.5 years ago, and it went very well. Another image to show that there are many people who work on this project, and here it was a particular test to check how clean was the spacecraft from an electromagnetic point of view, because we are going to make very sensitive measurement of the magnetic field, very important for the science, and you needed to have a spacecraft as clean as possible, and that was an image taken after a very important test to clarify that. So just to show now how JUICE will travel in the solar system, so we launched in April this year. And we cannot go directly to Jupiter because JUICE is too heavy, it's 6 tons. So before we have to do a few orbits around the sun and to do gravity assist. Here it's a gravity assist that will happen next year. So we pass via the moons, and then we go to the Earth. That's the first time we'll do an Earth-Moon gravity assist. Then we continue the orbit around the sun, because we still don't have enough energy to reach Jupiter. We go via Venus. Venus, very interesting because it's a big planet. So we take some energy from Venus, and then we can gain a little bit of velocity to go to Jupiter. So that's the second gravity assist. Then we go a little bit outside the Mars orbit. In the asteroid belt, we do another Earth flyby. Here we missed the moon, unfortunately. Another orbit around the sun. Still the asteroid belt. Hopefully will not will not impact an asteroid on our route. And then that will be the last Earth flyby in 2029. So you see how long it takes to orbit the sun and to get enough velocity to reach Jupiter. And finally, after January 29, we can be in the direct route towards Jupiter. So that will be the final pass, so 3 more years. Again, we go through the asteroid belt. Hopefully there will be no asteroid on our way. Then we go to around Jupiter for the orbit insertion. We switch on the big engine to brake JUICE, because JUICE will have, at that time, a lot of velocity, and then we need to decelerate to be able to be captured by the gravity field of Jupiter. We do first a gravity assist flyby of Ganymede to still reduce a little bit the velocity, another special things from the navigation point of view. And then we will be mainly in the equatorial plane of Jupiter to do flybys of the icy moon, so Ganymede, Callisto, and Europa, for more than 3 years. So every time we do a flyby, we'll switch on all the instruments and do as much measurement as possible, so cameras, images, measurement of the magnetic field, the radar, radio science, and so on. So here you will see an example of a Europa flyby. There will be 2 Europa flybys in 2032. Only 2 because Europa is relatively close to Jupiter, and it's not good from the radiation point of view, so we can only organize 2 flybys of Europa. Then there will be flybys of Callisto. Callisto is very interesting because it seems it's a dead body, so with no activity in terms of geology, but we might get some surprises from Callisto, and we would like to understand whether there is liquid water underneath Callisto. And if there is liquid water, it will be very interesting to understand why. Here we change a little bit the trajectory to go over the poles of Jupiter to observe the aurorae that I was showing at the beginning of the presentation. So for 6 months, we'll go above the equatorial plane of Jupiter, doing a lot of flybys of Callisto, and then at the end of the mission, we go into an orbit around Ganymede, which is the biggest moon in the solar system, and it's the main target of our JUICE mission. So we want to know everything about Ganymede. Is it an active moon? Where is located the liquid water? At which depth? What is the composition of the liquid water? What is the structure of the interior? And in other words, how is this possible to have habitable conditions inside a moon like Ganymede? So we stay a few months around Ganymede. We change the orbit from time to time. We go as close as possible. And at some point, when the mission will not work anymore, either because no power anymore or something does not work anymore on the spacecraft, at the end, we will crash on Ganymede. So that will be the end of the mission for sure, a crash on the biggest moon of the solar system. Here I got also many questions about the deployment, because shortly after launch we had a problem in deploy one radar antenna that caused a lot of headache, because without the deployment of this antenna we could not sound the first kilometers of ice, and that's the main investigation of JUICE. But after a month we managed to find a solution, and thanks to the big team of engineers and industry, we could find a solution to deploy this antenna. But that was also a big headache for us. And I think I am almost at the end. So I would say thanks for your interest in the JUICE mission. Even if it's a cruise phase, keep us joining on the ESA JUICE website, Twitter. We'll explain what we are doing. There is a gravity assist every year for the moment, so images of the moon and Earth are expecting. And then we'll cross to Jupiter, and we'll keep you informed until 2031 for the main part of the mission. Thank you very much.
Thank you very much, Olivier, for that amazing talk and important mission update. Going over to the dark side to talk about an entirely different mission. Please welcome to the stage Guadalupe.
Thank you so much for the nice introduction. Nope. Right here. Yeah, let's go. Nice. Okay, so I was saying that thank you so much for the introduction. And as a movie explains sometimes, better than just having a person here talking, talking, and talking. Just want to give you a sneak peek of what the Euclid mission is about. So please watch and listen carefully.
In 1915, Albert Einstein astonished the world with his general theory of relativity. It described the behavior of the entire universe based on the matter and energy contained within it. The theory sparked the modern discipline of cosmology and the hope that we would finally understand how the universe came to be. But in recent times, the effort to define what the universe is made of has given us a very big surprise. Visible stars and galaxies make up less than 5% of the universe's total matter and energy. Beneath this visible layer is a mysterious celestial realm, consisting of shadowy particles and unknown energy fields. For decades, astronomers have puzzled at their nature, calling these elusive substances dark matter and dark energy. ESA's Euclid mission will go in search of the answer to the fundamental question: what is the universe made of? A European-designed mission, Euclid is built and operated by ESA, with contributions from the International Euclid Consortium and NASA. ESA selected Thales Alenia Space to lead on building Euclid, with Airbus Defence and Space providing the telescope and payload module. The telescope and scientific instruments form the heart of the mission. Together, they will observe billions of galaxies over more than 1/3 of the sky. Producing record quantities of data, Euclid will enable scientists to draw a precise map of the universe across space and time. This will allow researchers to investigate the effects of dark matter and dark energy on the apparent shape of galaxies and on their motion and distribution over immense distances. In turn, this will help reveal the true nature of dark matter and dark energy. The spacecraft and data communications will be controlled from ESA's European Space Operations Centre in Darmstadt. To cope with the vast amounts of data Euclid will acquire, ESA's ESTEC network of deep space antennas has been upgraded. These data will be analysed by the Euclid Consortium, a group of more than 2,000 scientists from more than 300 institutes across Europe, the US, Canada and Japan. Understanding the elusive nature of the universe has drawn astronomers throughout history. It remains one of the most challenging investigations in modern science, but Euclid is up to the task. The Euclid mission is a quest into the unknown, a mission to shine a light on the dark side of the universe.
So I've seen this trailer, probably, few percent of the reproductions in YouTube are actually coming from my site. But we already have some spoilers about Euclid on this video. But Euclid is basically a cosmological mission. So what we are aiming is to understand what is the structure on the components of the universe. So we already know, thanks to previous observations, that our universe is dark. And with this, what we mean is that the main components, the main ingredients of the universe are actually substances that we don't know anything about. Less than 30% of the universe is some kind of matter, that it doesn't interact with light, and this is why we call it dark matter. We also know that our universe is accelerating, and that the expansion of our universe is accelerating due to some mysterious substance that we call dark energy. But just few percentage, 5% of our universe is the matter that we are all made of, stars, galaxies, and the rest of the visible things of our universe. So this is a real challenge. Cosmologists like me, we are able to actually give you with a really high precision the percentage of these dark ingredients. So as you see, 70%, slightly less than 30%, but we don't know anything about them. And this is what basically Euclid is going to be focusing on. Euclid is going to take pictures of more than 1/3 of the sky to look for galaxies. And basically, it's going to be focusing on galaxies between now and 10 billion years ago. By studying the distribution of these galaxies, the shape and the distance to those galaxies, we can actually reconstruct the timeline of the universe. And we can actually measure this rate of the expansion that we know that it is being accelerating. So thanks to understanding how the universe behaved in the past by other European Space Agency missions, such as Planck, we can say something potentially about how this ingredient and how matter is distributed over time, thanks to where galaxies are distributed now. So we launched back on the 1st of July, after some delays, after more than a decade of planification preparation, but we actually launched from Cape Canaveral, as I said, on the 1st of July, in a collaboration with SpaceX, a really big achievement for the Euclid mission, but also for the big scientific collaboration that is behind it, that I will tell you a little bit more in a few seconds. So Euclid is meant to join, actually already joined, some of our other astronomical missions, James Webb and also Gaia, in a special Lagrangian point, and a special point in space which is between the Sun and the Earth that we call Lagrangian point 2. It's a really popular point in our universe, a really popular neighborhood, because it allows us to take really good astronomical observations. So right now, Euclid is in the phase in which it has reached its final destination, and it has started to verify that everything works. That means that we have switched on the satellite and actually is ready to do scientific observations. So once that we have verified that actually Euclid can fulfill the role that actually can start taking astronomical observations, the goal of Euclid is actually create a survey. This is a different with respect to other observational astronomical missions, in which Euclid is a survey mission. It has a clear goal. And this goal, as I said, is to take pictures of more than 1/3 of the sky. So basically, the areas that you see here surrounded by the green lines. Other regions that we cannot actually, well, other regions that we are not planning to take pictures from, which are right in the middle of this plane, is because they are contaminated from our Milky Way light. So it's not actually that we are not ambitious. It's just that we are looking for the portions of the sky that meant served our role. So as I said, the goal is to map the universe. So map how the structure of the universe looks like. And how are we going to do that? So practically, so what we do is that we take a picture of the deep universe, and then we actually measure the position, the shape, and distances to galaxies. As nothing can go faster than the speed of light, we can actually classify galaxies based on the distance. And classifying based on the distance will allow us to access this third dimension, this temporal dimension, so that we can actually reconstruct how matter has evolved over time. So the Euclid spacecraft, as you can see, is basically meant to be a telescope, that it has to be in space, and it has to be basically fooled by the solar energy. This is why it has a really big solar panel. Euclid is quite big. I was actually able to be close to a spacecraft, and taking into account that I'm really small in a country such as the Netherlands, I found it really big. But actually, Euclid is a really massive telescope. There is a really big plan behind making Euclid a reality. The goal of Euclid is actually really ambitious. And this is why more than 300 institutions, 21 countries, 80 companies, so many different industrial contracts, more than 3,500 people, and yeah, some important money budget were meant to be included so that we could make Euclid a reality. And in particular, I'm going to focus just for a moment on these 3,500 people, because Euclid is going to take the largest amount of data that it has ever been taken for astronomical observations. And that means that it needs a really large number of scientists. And this is the role of the Euclid Consortium. This is the scientific collaboration that has more than 2,700 scientists that right now they are already busy understanding and reading and collecting their first Euclid data, with more than 14 European countries, plus the US, Canada, and Japan. And they are also responsible of having the two instruments on board. But now, let's talk about the funny part. What amazed all the scientific community of Euclid to be astonished like a few days ago. So as I said, Euclid has 2 instruments on board, and we have already tested how these instruments behave on space, and we have the first images. So let's look at them. This is how we can actually be able to see the universe, the really deep parts of the universe from the ground, from Earth. This is a real picture. And sorry, this is how we see it with Euclid now. So as repeated again, because sometimes 2 is better than 1, let's do it again. So this is a real picture from the DESI instrument on the ground Earth. And this is how we see it with Euclid. So Euclid is designed to actually provide really sharp images of galaxies, because this is exactly what we are looking for. We are really looking for really deep galaxies that are really far away, so we can actually measure their position and shape. But what I showed you is just a portion of the real Euclid images. What I showed you was just one of these 4 panels, when in reality, this is the exposure that Euclid takes with one of the instruments. This is the visible instrument, this. And this is how it looks like with the other instrument that we have on board, and we are actually using it to measure the distances to galaxies. So this is what we call the Euclid first light. So please keep tuned, because Euclid is going to give us most of the cosmological information and results for the next decade to come, at least in cosmology. And so many different news will pop up, especially the first, hopefully, analyzed data release of data release in 2025. So thank you so much.
Wow, those images are truly something. Even those early commissioning images are just a fraction of what is possible as the mission continues. So I'm very, very excited to see what comes next. On the theme of images, and you've probably seen some very, very beautiful ones. I'm not going to give any spoilers away just yet. But please welcome to the stage, last but not least, Mark McCorain is giving the James Webb Space Telescope mission update.
Thank you, Nicole. Thank you, everybody. It's a pleasure to be here to talk to you about something that's been going on for a very, very long time, and much longer than you might even think. So let's see. Righty-ho. So I'm going to talk to a project that I've personally been involved in for 25 years, but actually it's been going on even longer than that. So this is the launch of the Hubble Space Telescope in 1990, so already 33 and a half years ago. But when we launched the Hubble Space Telescope, we knew that it would be amazing, but we also knew that it wouldn't be enough. It would not be able to answer certain questions about the universe. It would take us a long way. For example, investigating the distant universe, seeing objects that are very far away from us and very far back in time, as Guadalupe mentioned. But we already knew that because the universe is expanding, that light from the distant universe is stretched out to infrared wavelengths. Hubble is a visible wavelength telescope. We knew that we would need to go to the infrared in order to be able to see the most distant galaxies furthest back in time. But at that point, infrared technology was nothing like as good as visible light technology, the kind of normal cameras you take pictures with. We only had the very first cameras for infrared pictures in the middle of the 1980s. And so this book was written here. This was the first description of what you would want to build as a machine to take us further back in time to see the very first stars and galaxies that formed in our universe. And you can see the date on it. It says 1989. So that was even before we launched the Hubble Space Telescope. So there, what I'm going to do now is compress all of time to show you the real machine. This is what we built. It's now called the James Webb Space Telescope. It's a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. It has a main mirror, which is 6.5 meters across in these 18 pieces. It's folded up here on the sides, but then the big sun shield underneath, 22 meters long, the size of a tennis court. So when you look at the model in the back of the room here of JWST, imagine the real thing. It fills a tennis court, and you're sitting in the tennis court here. So it fills the entire space that you're sitting in right now, the real JWST. So that was in 2019, on Christmas Day 2021, we launched the James Webb Space Telescope into space on a European Ariane 5. I was lucky enough to be standing not quite this close, that would be dangerous, but 5 kilometers away. My wife is probably in the room. If I say it's the best Christmas I ever had when I wasn't with my family, that probably won't go down so well. But it was a pretty amazing Christmas, let's put it that way. And I didn't even think I would be able to go. The launch was postponed and postponed due to weather and technical things. I wasn't even thinking I was going until the 22nd of December, because all the VIPs said, no, I'm not going to a launch for Christmas. I'm going to be at home. And I said, I'll go. I've been involved for more than 25 years. So we launched it on that day, and a few minutes later, one of the things that was really important was to unfold the telescope, get it away from the rocket. And this is the last picture we've seen of the James Webb Space Telescope where we can see it more than just a point of light. It's all folded up, as you can see here, and it's moving away. That's the Gulf of Aden here. You can't really see it on the picture so well now. And when the solar panel unfolded, and we saw it live on TV, everybody went completely nuts, because you need power on your spacecraft to make it work. And if it didn't unfold, we would have been dead in the water. Now, what happened next was to actually unfold it. It was all folded up to be in the rocket, and we had to unfold it. That took more than 3 weeks. Everything was incredibly painstaking, very slow, every cable, I'm going to show you in 15 seconds. Can we put the volume up, please? So that huge machine deployed all on its own with commands from the ground, and it was where many of us were very scared, because nobody had deployed a machine that big in space before, and much of it's floppy. Those big sun shields on the back, it's not kind of a hard structure, click into place. It was all floppy and all had to pull out on cables, and it worked astonishingly well. And just a few months after that, we were in a position where we had the first Starlight, where we had fully focused the whole thing. And actually, this is the point now we're seeing JWST images, where I'll ask John to drop the lights. Health and safety, who cares? Well, if you put the lights down, you can see things a little bit better. So this is a fully focused image from that full 6.5-meter telescope. So we knew we were in business. We needed the sharpest possible images to see the faintest possible objects far out in the universe. And since then, we've been doing science. Since the summer last year, when we released the first images, we've been doing science non-stop with JWST. And I'll just show you a couple of examples of that. So, for example, we've been taking pictures of the distant universe. This is the first image on the left-hand side, unveiled by Joe Biden on the 11th of July. And in the middle, just another galaxy field with galaxies everywhere strewn around. And then this is one of what we call the very deep fields. These galaxies you see on this side, some of these are close to us. They're big. Some of them are further away. Some of them are just points of light. But they're 13.5 billion years old, just 300 million years after the universe began. So we're already achieving one of the key goals we set for this observatory, to see the first stars and galaxies in the universe. So it's been astonishing seeing it achieve this. We've also looked much closer to home. This, for example, is the planet Neptune with its rings. Everybody thinks that it's just Saturn that has rings, but Jupiter has rings, Saturn has rings, Neptune and Uranus all have rings. It's more common to have rings in our solar system than not. This spectrum, which I've just turned on its side here, this is a planet going around another star where we've measured the atmosphere of that planet. So this is what we call an exoplanet at great distance from us. And we see water and sodium and carbon dioxide, carbon monoxide. We can measure the atmospheres of distant planets. And then this, on the other hand, is a dying star. As two stars together come close to each other, it throws off shells of dust every few years, and these shells expand out. Utterly beautiful. And some of the most famous images already from the James Webb Space Telescope are these. These are some of the star-forming regions in our Milky Way galaxy where we live. The Carina Nebula, which was released on the 12th of July last year. The famous Eagle Nebula, which is very famous from Hubble pictures, which of the same region but look very different. And then this object, VLA 1623, this was on the first birthday of JWST's first images. But the most famous star-forming region in our nearby universe is this one, Orion. So this is the constellation of Orion that you would see in the nighttime if you go out in wintertime here in the Northern Hemisphere. Orion with his two shoulders, his feet, his belt, the three stars, and hanging below the belt is the sword of Orion. And you can see down there where it says the word sword, there's a patch of bluish gas and dust. And that's the nearest region to us where young stars are forming with very massive ones, 50 to 100 times the size of the sun, all the way down to very tiny ones. And with visible pictures, you really can't see them very well because there's so much gas and dust in this region that obscures the stars. You need to do this in the infrared. You need to peer through the gas and dust and see the stars. So this is where I started my academic career in the 1980s with the first ever camera designed to take pictures in the infrared for astronomy. And this is the picture from my PhD thesis of just that little section down there. It was a long time ago. Don't laugh. I got a PhD for that picture. Well, a lot else went into it, but this is a black and white picture, a single wavelength of just that tiny little box down in the corner. And you can see now there are lots and lots of stars crammed in there. The distance from one side to the other is about the same distance as from us to the nearest star, Proxima Centauri, for us. And it's full of thousands of stars in Orion, all densely packed together. And they're just 1 million years old. Much, much younger than our solar system. A year later, I was able to go back and take the first color image. So now we're beginning to see some red stuff at the top, some blue stars, and different colors in the mosaic. And my career, along with many other things, has been going back to Orion time after time and saying, let's put the best technology we have to see what's happening in Orion. So just last year in October, we went back with the James Webb Space Telescope. I'm a member of the science team for that mission. I said, that's what I want to do. I'm allowed to do that. We went and we took this image. So that's the Orion Nebula in the infrared with the James Webb Space Telescope. Everything's super sharp now, seeing much more detail. And we'll zoom out. But what I'm going to do now is an experiment. I have a few minutes left, because what you can't see is all the details. This is a fantastic, beautiful, lovely picture, but it's when you zoom in that you see the most amazing things. So let's see if we can make this work. There we go. Good. Let's get rid of this. So, same picture you saw before, but let's zoom in. That's the center, the trapezium stars. These are the very bright stars at the center, the very big, massive ones that are throwing out lots of ultraviolet light and heating up and illuminating the whole nebula. So as we scroll around, we see all sorts of young stars. They always have these spikes with JWST because of the hexagonal mirror. And we see material flowing out from new stars. So these red regions here are places where there are young stars, which we can, just off the bottom of the picture, throwing out material. And if we scroll up, I should make a movie out of this, and I will, but this picture was only released on Monday, so it's been a bit of a hectic week. How about that little object there? That is a forming solar system in the Orion Nebula. The dark patch is a disk of gas and dust spinning around the young star, making planets today, but that disk is being blown away by the bright light from the stars down off the corner. So we see these all over the Orion Nebula. We see young planetary systems being made today. And if we zoom back out from there, you'll see that it's invisible as a dot. So if you pick up the posters, which are at the back or elsewhere, remember that that object is actually in there, right in the middle. And if we go up here, for example, this is a massive young star being born in the Orion Nebula today, and there's a big explosion took place about 500 years ago when two stars came together and crashed and threw out enormous amounts of energy, and this flowing material is expanding out at hundreds of kilometers per second, and we see the shrapnel, the bullets from that explosion, screaming out into space. So this is really new stuff, fresh just this week, and I've been working on it all summer, no summer holiday, 7 days a week, non-stop. So I'm happy I got it done in time for the open day, because to share it, you're the first people, if you've seen it in the news, you've seen it in the news, but you're the first people to hear me talk about this. And I'm pretty excited by what we found. But there's one more thing. So if we go down over here into this corner, again, these are the big bright stars illuminating. You can see these with the naked eye, but millions of times fainter. So up here, we have these beautiful places where the gas and dust is being evaporated and burned away, these beautiful features, giant pillars of gas and dust being blown away by what's hitting them, the ultraviolet light. But just beneath there is a lovely group of really interesting little objects. Now, you might just be able to begin to see them on the screen, but I'll zoom in a bit closer. You see all these things that are double? Here, 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 and there's another one off the side. Little binaries. But these things aren't stars, they're planets. They're the size of Jupiter at the back of the room. So these are binary planets floating freely through the Orion Nebula. And we call them Jupiter mass binary objects, or jumbos. It's a nice name. Everybody likes an elephant. Jumbos. So we discovered these jumbos, and there was a lot of press coverage this week. We've got to go back and take proper spectra of them to measure their chemical properties and their physical properties. But this is totally unexpected. Nobody expected to be able to make little binary planets floating around in the Orion Nebula. So even in the first week of this, we found so much, and we have so many more things to look for. I mean, just because I have the podium, how about this as another little solar system in the making? Just 1 million years old, roughly 10 times bigger than our solar system. You can't see the star in the middle because the disk is edge on to you. So the star is blocked by the disk, and that disk is forming planets today, more planets. That's what we looked like 4.5 billion years ago. So it's a baby picture of our own solar system in some way, if you like. Now, just to jump back into the presentation for the last 2 minutes, you can get these posters. They're all around, hopefully, and I'm very happy to sign some for you after this session. But that's not all there is, because when we did this, we actually took this data in lots of different wavelengths. There are 6 different wavelengths put together here, but we also have another 6. There's the tour. We go back to that image. The other 6 look like this. Exactly the same region. Now we're seeing the gas and dust in a very different way. We're seeing molecules which are made out of hydrocarbons, the stuff that our starches and our food are made out. All this green stuff is hydrocarbon molecules. So we've just started. We've just taken the data last year. It's taken us all year to get it. We're writing papers. I'm happy to share that excitement with you. I hope you can hear what a thrill it's been to work on this, and a privilege. And just to, if you put your phone up now, or you can find the QR code elsewhere in the room, you can go and download these images in the full size, 21,000 pixels wide, and you can explore them and go and find things. And if you do, and you want to put that on social media, hashtag Pieces of Orion. If you find something exciting, something interesting, just tell us, because we haven't found everything in there so far. So please have a look. And please come back again next year and hear from some more of my colleagues who spend their lives building these amazing space missions. This is one of the longest that it's ever taken, more than 35 years. And I said I started with my PhD. Well, I thought I would share the fact I did have hair once upon a time. So this is me 1 minute before the defense of my PhD thesis, revising. The big book is my PhD thesis. And now, with the James Webb Space Telescope near the end of my career, it's been a privilege, and you've made it possible. Thank you.
Wow. I think I can speak for everybody when that's pretty much all I can say about the matter, because it's really, really impressive. I mean, this is just, we're not even scratching the surface of what these images, of what these spacecraft are capable of taking. And these are just beautiful, beautiful images. And I hope you'll remember this day. And if you like, as Mark said, we've got posters at the back of the room. You can take a piece of the mission home with you today. So thank you all very, very much. today by none other than ESA para-astronaut Jon McFall. So please, yeah. Jon. So.
Hi.
Hi,
Nice
lovely
to be
here, and lovely to meet you on stage. This is fantastic. So, spaceflight, the next generation. I wanted to talk a little bit about, first of all, the ESA astronaut call, the recent astronaut call, and how you entered into that, how you found out about it. So when did you first have a look at the call, and were you contacted directly, or did you see it online?
I was working peacefully and quite happily as a trauma and orthopedic surgeon in the UK, and I had a message from a friend of mine who I worked with, and he was like, Jon, they're looking for Paralympians to go to space. And I was like, what? That sounds weird. Some crazy experimental project. But he was right. And I looked up, I did a quick search, and ESA had put out a vacancy notice looking to recruit in their astronaut selection in 2021-2022. They were looking to recruit alongside the regular corps of astronauts. For the first time in the world, any agency wanted to recruit someone with a physical disability, to see if it was possible to get someone with a physical disability to train for and live and work in space and fly on a long duration mission in space. So I looked at it, and it was just right up my street.
And I think we have an image we can show on the screen that actually shows the call for the para-astronauts. Can we display that, please?
There we go.
There we go. There it is.
So yeah, this was the vacancy notice that went out, and initially they were looking for, they could have had all disabilities, right? But that possibly would have been biting off a little bit more than we could chew. So they had to scale it down and look at, okay, what do we think is going to be feasible and not really a huge departure from able-bodied astronauts. So it was amputations, either single leg or both legs, leg length discrepancy, and short stature.
Sure, and of course, that's not to say that in future we wouldn't be considering more or a wider range of disabilities, but with these things, you kind of have to start somewhere.
Yeah, exactly, and I'm very conscious that my disability is only a very small representation of the whole spectrum of disabilities that there are. But actually, we've got to start somewhere, as you say, and I hope that this will be the first step in a much bigger journey in creating a legacy for understanding this a bit more.
And I think we're really leading the way in this, and it's totally groundbreaking. But I just wanted to talk for a moment. There are, not many people know about this, but there are kind of two sides to doing this para-astronaut study. One of them is yourself, is the para-astronaut fly, it's called. And then there's the research activities, which is what I'm involved in coordinating. So there's a group of researchers, and they're called the Para-Astronaut Topical Team. And what their research will do is they'll look into all of the different elements that are to do with making a para-astronaut a real possibility, looking at it from a socioeconomic context, and looking at it also physically and from a medical context. And one of the ways that the community is doing this is by actually working with what we believe are the experts. So there's this fantastic organization in the UK, and they're called Airability. And their mission is to get as many disabled people flying as possible. And people with disabilities are joining this organization and going right the way to many actually completing their pilot's licenses. And this is something that's really exciting, and we're consulting experts like this so that we can think about things right before we get off to a start. So I remember in the last meeting we discussed like real accessible flight and what that means, and there were considerations to take into consideration things like exit rows. You know, like on an aircraft, if you're in the emergency exit row, someone might come round to you and say, are you able to exit this aircraft in the event of an emergency? And there's almost a direct translation from that to spaceflight. And so there's all of these things that we need to consider. And I just wanted to ask, is there something that jumps out at you immediately that crosses over from the terrestrial world to space?
Yeah, absolutely. And do you know what? You can stick anyone in a rocket and stick them up in space and they can fly and float around the International Space Station. And this is what in the space industry we call, there is nominal, which is normal scenario, like when everything goes well. So when everything's going well, you know, that's fine. The issue comes when things don't go well. So when there is off nominal. So, and this boils down to emergency procedures. And this tends to be really that we've identified where the issues are probably going to be the most significant, not necessarily for me so much, but actually looking at the wider disabled population. So that's, I think, from emergency scenarios. So, for example, can someone who is a wheelchair user do CPR in microgravity? Things like that. In an emergency situation, if there is an emergency on the launch pad and you're in the capsule, can someone egress the capsule quickly, get down the crew arm into the basket and off to a safe place around the launch pad? You know, and if we're looking at a wider range of disabilities, we have to consider these emergency and contingency plans. But I wanted to pick up what you said about Airability, and I know these guys at Airability. I've flown with them, and awesome guys there. Really inspirational. But do you know what is core to this? What is really core to this is what Mike Miller-Smith and the guys working there have done, which is challenging, so working with the UK Civil Aviation Authority and challenging what is possible and saying, listen, I know you have these rules for people getting their pilot's licenses, but we also have people with disabilities who can fly. Let's work closely together with each other and see if we can't get people to get their private pilot's licenses. And so this has been really progressive, open communication between organizations for the benefit of a wide range of people.
It's really moving in such a good direction, and I'm so hopeful for the future. You mentioned that anybody could be stuck into a rocket and sent to space, but that's actually not what we're recruiting here. We would like to recruit career astronauts, and that means doing all of the other tasks that astronauts do, and that's sometimes being an engineer, sometimes being a scientist. Are there any elements of that you're particularly looking forward to?
All of it.
All of it. Soak it up.
Yeah, I mean, for me, one of the reasons I got into this role was because I was hugely passionate about learning and hugely curious. And I think there aren't many jobs which involve so many aspects of, you know, the scientific community and curriculum, if you like. Yeah, I mean, a lot of it.
That's fantastic.
Sorry, I couldn't be more specific.
No, it's great. It's great that you're enthusiastic and that I can steer you towards some of my own experiments when they eventually fly.
Yeah.
But I wanted to talk next a little bit about training, and I think I've got a video. I think this is the video of you on a parabolic flight. I think that's. Is it playing now? It might be click twice. Or click many times.
The next thing
here we go.
Is zero gravity. Now we will have a series of 4 parabolas, the same timing that we had, but 4 instead of just 3. They will all be zero gravity. Okay? So at the beginning, we recommend you take it easy, just learn what it feels like. The process is the same. The hypergravity is the same. You know how to do that now. Lay down, keep your head still. Before and after. The 0G is different. It's definitely different. You will notice.
Allez, on reste calme, Jordan, comme tout à l'heure, c'était très bien. Oui. On essaie de... Allez, on essaie de pas se débattre. Waouh. Ah, je pars dans tous les sens là. Tu restes là, c'est bon? Ouais. Attention, on va descendre là. Ouais, Jordan, c'est bien. Doucement, sorry. Nice. Doucement. Allez, allonge-toi doucement. Et bouge plus là, ça va.
So it looks like you were really enjoying yourself. You were really enjoying yourself.
I do somewhere as well.
Allez, on bouge pas. Attention.
Hey, look at the camera. Stay attached.
Yes, regarde devant. Yes.
Hello. Look at the camera. We fly.
Regarde devant.
Or we can just keep talking while the video plays, that's also fine. I've also done a parabolic flight. It is an incredible experience, isn't it? And this was your very first one. Tell me how that was for you.
I really enjoyed it, and thankfully, it turns out I'm not the kind of person who gets sick on a parabolic flight, so otherwise it would have been a bit embarrassing.
Yeah, they call it the vomit comet for a reason.
Yeah, being recruited to the space agency and not being able to tolerate a parabolic flight. But it was great fun, and I learned a little bit about, although it was quite brief, how to move around in reduced gravity, how to move around in microgravity. And you may have seen there, actually, when I was floating, my leg stays out straight. And if you watch gymnasts or divers or ice skaters, when they do tumbles or they spin on the ice, to tumble quickly or to spin quickly, you bring your limbs close to your body, and then to slow yourself down, you put your limbs out like this. It's called the conservation of angular momentum. And actually, having my leg out straight in front of me makes it a bit trickier for me to forward roll as quickly because of that extra inertia required to get round. So that's something that I picked up on that flight that might be something to address and practice on subsequent parabolic flights, and think about actually if I do fly to the ISS and spend a significant amount of time in zero-G.
Yeah, it's quite incredible to watch and to experience yourself, and not just the microgravity, but also what I found interesting was the hypergravity. I really wasn't anticipating that. So on a parabolic flight, you have a period of hypergravity, you have almost 2G, and you feel very, 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 very heavy. And then once the aircraft goes into the injection phase, into 0G, it's just gravity switches off. So you go from feeling almost double your weight. So if you're 70 kilograms, you're feeling 140 kilograms, and then nothing, weightlessness. And did you find that any kind of, did you find it difficult to adjust to the hypergravity?
No, so at the beginning, the biggest issue with hypergravity, or they say they call it the vomit comet, and they call it the vomit comet not because the floating makes you sick. It's actually the periods of hypergravity that make you sick. So it's the 2G. It really messes with your vestibular system in your ears and makes you feel sick.
And you're doing so many of them again and again and again.
And again. But actually, by the halfway through, I was in the 0G, and then I would come out of the 0G onto my feet, and I would stand through the 2G phase, and then I would go up again.
That's pretty impressive.
So that was, that for me, I felt I was quite comfortable with that. But initially, they tell you to lie on your back, because you saw them all lying on the back, keeping your head still, because apparently, if you move your head, that's the thing that makes you feel sick.
And also I was told facing down towards the aircraft cabin and not on the side, but I was doing an experiment where I had to be on the side, but I felt okay as well. The hypergravity was definitely a bit of a shock. So this was your first time in 0G. What other things have you been doing? So have you begun astronaut training then, formally?
So I'm not formally doing the basic training along with the other astronaut candidates. However, there are some aspects of basic training that overlap with the requirements of the feasibility study. So things like sea survival training. So I have been on a sea survival training course. And
is that the one with the helicopter as well?
So not yet. So the helicopter is more the mission-specific one. This is where you're dropped in the water and you have to turn an upturned raft back over the right way and get into it and that sort of thing. And some basic sea survival skills. So that was part of the feasibility study, which is an important if you have a situation where you accidentally end up unsupported in the sea.
Yeah, it's pretty amazing. And did you do anything to do with sailing, or did you do rowing, perhaps any kind of water sports before you started this?
No, I would swim, but other than that, I wasn't a sailor or anything like that. So yeah, being in the water like that was not as familiar for me.
But of course, as a Paralympian, you've got these amazing swimming skills, so
well, yes.
Give it a shove.
Yeah.
I think you'd be all right. So I think we can take a couple of questions from the audience. If anybody has any questions, we've got a microphone that's going to go around. A trusty assistant.
Hi, John. Can you tell us about the day you found out that you were selected and what that was like? What it's like in that moment when you realize your life's just going to change forever?
Well, yeah, I'd spent the day tidying the house, being the good husband. And I'd moved a lot of stuff around. And to reward myself, I went over to my brother-in-law's house to have just a beer and a catch-up and a chat. And whilst I was having a chat with him, my phone rang in my pocket. And I was like, oh, sorry, it would just be the wife calling me to say, John, where have you put this? Or something, because I tidied loads of stuff away. So I ignored it, as you do. And I said, I'll just finish what I was saying to my brother-in-law, and then I'll have a look who it was, because I didn't want to be rude and interrupt the conversation. And then I pulled my phone out after I'd finished this part of this conversation, and I was like, oh, it's a call from Paris. And I was like, oh, maybe that was the DG. And then literally as I was doing that, 2 minutes later, he phoned back again and said, John, thank you very much. We'd love you to come to Paris to be part of the new cohort of astronauts. Yeah, I was hugely proud, and it's a long process. It's about 18 months from the day you press that button online to send your application off to the Director General saying that they want to recruit you. So I was proud and excited.
It's not a phone call that you get every day.
It's not, no.
Wow. Are there any more questions in the audience? If not, I've got one that I would like to. There's so many things that I would love to ask you, but I feel like I'm stealing time away from everyone. So in the course of the astronaut training, so you've already done the survival stuff on water. What's the plan for the next? Can you say 6 to 12 months? What's coming up for you?
Yeah, so we're going to look at things that we've identified so far in the FLY study that we want to address further. And the main things are looking at getting prosthetic hardware certified, because I need to exercise on the ISS and I need to wear a prosthesis, as we discussed earlier, at launch. So we're going through a process of hardware certification. But we also need to understand as much as possible how much, so obviously being an amputee, I have about this much of my leg left, and I wear a hard socket. Now, the volume of my leg could change, and we don't know exactly how much it's going to change and necessarily which direction it's going to change. So will it swell or will it decrease in volume? And so we need to try and predict as best as possible what will happen and by how much, so that we can be prepared for when I actually do fly. So we're doing what's called a fluid shift study or a suspension study to try and understand that. And we think, based on what we know so far, probably, if anything, the volume will get slightly smaller because your circulating volume tends to go more towards your center because you haven't got gravity forcing it down into your legs.
And then, of course, there's other things that you have to account for, like muscle loss and bone loss and other things like that we use exercise as a countermeasure for.
Yeah, exactly. So, if my leg or my stump does decrease in size significantly, how are we going to mitigate that or solve that so that I can still do my exercise to maintain my bone density and muscle mass? And then we have the usual fun things like winter survival training somewhere in northern Sweden and things like that.
You might see the Northern Lights.
Yeah, we may do.
So it's not all bad. So in addition to the training, what about your friends and family back home? Like how are they taking this? Are they very excited for you as well?
Yeah, I think quite a few of my colleagues at work were a little bit jealous. I had a couple of colleagues who also applied but weren't successful. Those of you who don't know, I'm a medical doctor and orthopedic surgeon, and I work in the National Health Service in the UK, it's a great institution to work in, but it's not easy. And there are a lot of my fellow surgeons who are facing the day-to-day problems of working in the NHS and looking at me going off to do crazy, exciting things. So I think there's maybe a little bit of jealousy there.
Just a hint.
Yeah. But my family, very, very proud, very happy. I've got my wife and my 3 kids here who, for them, it's a great opportunity for them to see a different, live in a different country, be exposed to the great science and technology and engineering and the world of space. So that's, for me, it's lovely to be able to do that for them. Yeah.
Fantastic. I just quickly wanted to mention, yes, of course you have a medical background, and I wanted to say that is so handy for us because it's not like if you've got something going off on ISS and something's wrong with you, you're going to be able to just pop down the road to the doctor's office. To have somebody with the medical training on board I think is only an asset. And yes, of course, we have at ground control, we're going to have medical professionals round the clock available. But I think just having someone up there with the know-how is also.
Yeah, and on every flight there is someone who is assigned the medical responsibility for the crew. And again, that's another hat I can wear, and I can be that person already medically trained, which saves a bit of training and time. And to be able to look after the crew, my crewmates when I'm up there.
It sounds like you're poised to go.
Yeah, it sounds like I've already sent myself there. It's not for certain yet, but
so you're manifesting it.
Yeah,
it's fine. I can see that. And I think just finally, I wanted to say, or just wanted to ask, if there's any advice that you would give to somebody with a physical disability who is dreaming of becoming an astronaut, hasn't seen this opportunity before, is now seeing you, and maybe in the future they want to apply. What kind of advice would you be able to give?
I think it wouldn't be advice just to people with disabilities. I think it would be advice for everyone.
In general.
And I would say challenge what is normal. Challenge what has gone before. Is it right? Question it. Why can't we do things? And be open-minded. Be ready to explore what is possible. But also, specifically relating to disabilities, spread the word that, I want to increase or raise people's awareness and thresholds of maybe what they already think that people with disabilities are capable of. And I really want to raise that and demonstrate that they may actually be far more capable to do much more than we already think, and be open-minded to that.
For sure. Well, it sounds like the right stuff is moving in a different and much better and much more inclusive direction. John McFall, it's been a pleasure. Thank you for joining me on stage, and thank you for joining ESA Open Day.
Thanks very much.
Thank you all. Please. That's it for today. Thank you all very much for joining. I hope you've had a fantastic time visiting us here at ESA ESTEC Open Day, and I wish you safe onward travels.